these emissions not just stabilized, but down to zero. So that is the problem. And there are various estimates. You all have heard about the Paris Agreement and the hope to limit warming to 1.5 degrees. I think that's increasingly becoming out of reach. We already had 1.3 degrees, not quite yet an decadal mean as stipulated by the Paris Agreement. 1.5 degrees refers to decadal averages. But still, the 1.5 degrees warming we may well reach within the next 20 years or so, even on average. This may be difficult to avoid. At the time, the most recent IPCC report came out a couple of years ago. The estimate was that to avoid 1.5 degrees warming, we would need to reduce greenhouse gas emissions by 43% by 2030. And that's just exceedingly difficult, if not impossible. To limit warming to around 2 degrees, the Paris Agreement threshold, the IPCC estimated that the greenhouse gas emissions still should peak before 2025. They still haven't peaked. It's not clear they have peaked at least. And we would need to reduce them by roughly a third by 2030 to just have a 66% chance of limiting warming to 2 degrees. So even that is a very tall order and very challenging to achieve. Not impossible, but challenging. Drastic emission cuts would be required to limit warming to the threshold stipulated by the Paris Agreement. And what's even slightly worse is the following. If you just look at how much warming was produced by greenhouse gases over the last century, that's actually more than the warming we have seen. So this is again from the most recent IPCC report. The estimate is that roughly 1.5 degrees warming is what we should have seen due to greenhouse gases alone. We did not see 1.5 degrees warming yet because attendant with greenhouse gas emissions, they're emissions of aerosols, precursors of aerosols, gases that create air pollution. And that pollution, that smog, is reflecting sunlight, cooling the earth. It's also modulating cloud cover, likewise, probably cooling the earth somewhat. So there was some warming that was masked by greenhouse gases. In the IPCC report, that masked warming was estimated on average to have been something like 0.4 degrees perhaps, but with a large uncertainty. You see the uncertainty arrow bars on the left. There have been a few recent papers estimating that this masked warming has been even larger, which means that if we manage to get emissions to zero or to much less than what they are now, we'll have the attendant benefit of cleaner air, which is something we all should strive for because air pollution kills roughly 10 million people a year. Yet cleaner air will mean more warming. So if the warming that is masked is, say, 1 degree right now, and we don't know if it is, we would see that additional degree of warming on top of the greenhouse warming we have already seen in the coming decades. And that would make it even harder to stay below the 2-degree target. The uncertainties on these aerosol effects are very large. It's unclear how large they really are, but I think we cannot rule out that they are larger than they have been estimated to be on the basis of a number of recent papers by various groups. For example, estimating aerosol effects from ship tracks. So the best case scenario, we all need to learn to live with about 2 degrees global warming, I think. Now, 2 degrees global warming, they're not globally uniform 2 degrees warming. Yeah, likewise from the IPCC report, it's a multi-model mean of the warming, the global warming that you would expect to see when the Earth on average warms 2 degrees. But the warming is much larger in some parts of the world. For example, in the high latitudes in the Arctic, the warming in a 2-degree warmer world would be 5-6 degrees or so on average. And in fact, the Arctic, Canadian Arctic, for example, already has seen several degrees warming over the last century. In general, continents warm more than oceans for reasons we understand, having mostly to do with moisture supply. So 2 degrees warming locally means considerably more than 2 degrees in many parts of the world. Why do we care about global mean warming in itself? The global mean temperature is not what drives human impacts. However, just about any impact you look at is correlated with global mean warming. Here's, for example, the intensity of heavy rainfall in South Asia. So the vertical axis gives the rainfall intensity in monsoon regions where you are, and the horizontal axis gives the global warming relative to pre-industrial times. And you see that the rainfall intensity, the increase in rainfall intensity, correlates almost perfectly with the global mean temperature increase. That's ultimately why we care about global mean temperature. It's not the temperature in itself, but just about any impact you look at correlates with global mean temperature. And clearly, flooding from intense rain is something we do care about very much. We have already seen the devastating effect of flooding on humans, on human structures. Here's an example. This is Hurricane Harvey in 2017 that devastated Texas. Several independent studies have estimated that the probability of the rainfall that actually occurred during Harvey, the probability of that rainfall occurring, that rainfall intensity occurring, was roughly tripled by recent climate change already. And so more climate change, more global warming will make intense rainfall and floods such as that seen during Harvey even more likely. So it's absolutely crucial we do reduce emissions, but it's also unavoidable that we'll adapt to the climate changes that are already in the pipeline and that they're coming. And adapting means right-size our infrastructure such that it can handle storms such as Harvey, for example. We are not well positioned to do this quite yet. We have climate models that tell us that Earth is warming. They have been very good in predicting large-scale features of global warming. They have been very useful for scientific investigation, for example, allowing us to understand why rainfall intensity increases in a globally warmer world. But their predictions are not quite accurate enough to be useful for engineering purposes, for planning stormwater management infrastructure, how high a seawall to build, and the like. And there are two problems we have. Number one is the models themselves are not accurate enough. And I think a crucial reason they are not is that they have not used data to the extent they can. So there's a gap between the climate data we have, 50 terabyte per day collected by NASA alone, and models. Data have largely been used for model evaluation, much less for model training. And then there's a second gap in making output from climate models useful to people, for example, planning infrastructure, or just consumers wanting to know, wanting to contextualize. For example, where I am in Los Angeles, we probably had the hottest day on record today or something close to it. And so it would be nice to have tools for consumers like me that, well, A, can tell me immediately, is it the hottest day on record? Those tools exist, but then I'd like to know how many of those days will we have 10 years from now? In some ways, this is an extremely hot summer, but it's the coolest summer of the rest of our lives. And it would be nice to have tools in people's hands that immediately can contextualize weather events like this in the longer trajectory of global warming, neither of which we currently have. So as I said, models have been quite good at predicting large-scale features of climate change, but when it comes to usability for engineering purposes, they have severe problems. Here, let's go back to the global mean temperature. This is likewise from the IPCC report, a bit of a spaghetti diagram of global warming simulations with all the climate models that entered in the IPCC report. And there is a higher emission scenario in orange and a lower emission scenario in blue. And if you just focus your attention on the 2-degree warming line above pre-industrial levels, you see that the time when that threshold is crossed varies a great deal from model to model. It also varies a little bit across emission scenarios, but there is huge uncertainty across models. There are some models where allegedly the 2-degree warming line has already been crossed a few years ago. Now that's plain wrong. We haven't crossed that. And then some models where the 2-degree warming line would not be crossed even in a higher emission scenario by 2060 or 70, and anything in between. So this is too large a spread to be useful for engineering purposes. And that's sort of the first crux of the problem, is reducing these uncertainties, reducing and meaningfully quantifying them. Here we have uncertainties sort of haphazardly quantified by spread across models, but that's not based, for example, on observations or any true quantification of uncertainties. Just what the models may not span the true range of uncertainties here. Why are these models so divergent? The crux of the matter are small-scale processes, and first and foremost, among them, clouds. Clouds are the dominant uncertainty in climate projections. They cannot be resolved in climate models. A typical climate model has resolutions typically 100 kilometers, going towards 10 kilometers, a few simulations going to kilometer scale resolution for shorter periods. But all of these simulations are much too coarse to resolve clouds, and especially low clouds over tropical oceans, like what you see in the satellite image in the lower right. This is stratocumulus deck. You see these bright white lines. These are ship tracks where ships passed and emitted aerosols that brightened the clouds. There is no way that clouds like these stratocumulus will be able to resolve anytime soon. The dynamical scales of these clouds are meters, tens of meters. This is far smaller than the resolution of climate models, and the resolution is achievable in climate models in the foreseeable future. So these small scale processes are the crux of the matter: cloud dynamics, cloud turbulence. And when I started working in this area a number of years ago, I wanted to make sure that once I start working in it, scientists don't become obsolete too quickly. So I did the following synthesis of some data, some calculation. I compiled the world's fastest computer, the peak performance of the fastest computer going back to 1980 or 1979, which was the time of the publication of the first climate assessment. Peak performance of computers has doubled roughly every 1.2 years. And when I made this plot, what surprised me at first is that this exponential increase has kept pace despite transitions from vector machines to parallel computing and the like. In some ways, massive parallelism kept up the exponential increase even at the end of Dennard scaling. At the bottom is the AR1 to 5, marks the publication of the IPCC reports from assessment report 1 to 5. And here are climate models up to the point when I made this figure, 2017. And on the left axis, they're horizontal resolution. So this goes from atmosphere-only models and solid circles to atmosphere-ocean models and open circles, or system models, including a carbon cycle and diamonds. And it's likewise on the log axis. This is the horizontal resolution in inverse kilometers. So 10 to the minus 3 is a 1,000-kilometer resolution in the horizontal. And I plotted the left axis on the log scale, the right axis on the log scale, and I plotted them in just such a way that a factor 10 increase on the left axis corresponds to a factor 10 to the 4 increase on the right axis in flops, because if you want to isotropically increase the resolution of a climate model by a factor 10, you need 10 to the 4 times as many flops. Factor 10 to the 3 for a 3 space dimension, or a factor 10 for time. And what you see is if all increases in computer performance would have gone into resolution in climate models, the orange dot should lie on the blue line roughly. And they don't. They follow, if they follow any line, it has a shallower slope, which is to say the climate models have become more complex, but the resolution of the atmosphere models has not been maximized given the compute performance we had. Rather, we build atmosphere ocean models or system models and the like, more complex models that have elucidated a great many aspects of a climate system, and it was a good thing to do. But now you could do the thought experiment to say from here on, we only invest in resolution of climate models and say atmosphere and ocean resolution. So I suppose extrapolating from 2017, it would still be good if you do it today. So if we assume, somewhat unrealistically, that computer performance continues to double every 1.2 years for the next few decades. Few people believe that's doable, but let's just assume that could happen. Then the resolution of atmosphere models here would just follow the blue dashed line and keep increasing according to the blue dashed line. You can read off where we would be. So we are entering the gray zone of deep convection. So where deep convection becomes marginally resolved, 10 kilometers just about now. And in fact, that's what we can do now. We can now run simulations at roughly 10-kilometer resolution for decades. But if we want to get to these low clouds that are the biggest uncertainty in climate simulations, they have dynamical scales of tens of meters, 100 meters perhaps. They're not even on this plot. If you extrapolate this out, we can resolve those by 2060 or so. we would need roughly 100 billion times the compute we currently have to resolve low clouds globally. So with brute force computing as we know it, we're not going to solve that problem. That's in some ways good news. We need scientists like all of you to make progress, not just computers. In some ways, the problem is even worse. So I talked about the turbulence scales of clouds. They're tens of meters, perhaps. But below those turbulence scales, like yet smaller scales, there's the whole microphysics of clouds, how droplets form, how ice crystals form. We need to know the macroscopic effect of those microphysical processes in order to know the cloud albedo, precipitation, and the like. So what we have in a climate model are large-scale variables on a computational grid. Let's just say 10 kilometers we can do. We have humidity, temperature, winds, and the like. But what we really need to know is what's the albedo, what's the droplet size distribution in clouds, their precipitation characteristics, which depends on processes on micrometer scales. And from micrometers to 10 kilometers, there's no way by brute force computing to bridge those scales either. So you need to find ways of link what happens on the micro scale, what the effect of that is on the macro scale, to what we have available, which is fields like temperature, humidity, and such, on roughly 10s to 100-kilometer scales. Oh. So here is what we thought a number of years ago we have and what we can capitalize upon. We do live in the golden age of Earth observations. We have satellite data, for example, of clouds. Here is a curtain from a cloud radar from space, from the CloudSat instrument, overlaid with LiDAR from Calypso, with MODIS is yet another cloud observing satellite. For the first time, for the last not quite 20 years, we have global 3D data on cloud cover. It's not always the temporal resolution you like. These are polar orbiting satellites, but we have global coverage of cloud data that we should use. We also have computational capabilities. We can actually simulate clouds quite well, just not on the globe. Here is one example. This is a high-resolution large eddy simulation of clouds we did. These are Caribbean cumulus clouds. Blue is rain, gray is the cloud. And these are good simulations. This is a simulation of a field campaign where we have aircraft data. We can compare the simulation against aircraft data and have confidence that's quite a good simulation. This simulation has resolution of 5 meters in this case, which means there's no way to do this globally. So you can do it in small boxes. In this case, the box is a few kilometers on this side. So we can computationally generate data where we don't have observations. For example, about in-cloud turbulence, we have virtually no data. But we can computationally generate data that provides information and is useful for informing climate models. So Klima was founded in 2018. Yep.
What you really need is the reflectivity of the clouds, right? Not the detailed modeling. Can one kind
Say again, it's very echoey. I have a hard time hearing what you say. Say it again.
You say that what you need is the reflectivity of the clouds.
That's what matters for climate, yeah.
So is there a way to maybe make that a cheaper computation?
Is there, what was the question?
Can you do that more cheaply in your simulations? Not do this in-depth kind of detailed modeling?
So your question is, is there some sort of shortcut around simulating all the small scale turbulence to get at the macroscopic properties like reflectivity? We don't know of any such shortcut. So it would be nice if there were, but right now it's not known. And part of the difficulty is that, well, I'll talk a bit more about it, but we have actually very little data, even computationally generated data, to build, say, emulators that get you at these processes quickly. We have done a lot of work on generating data, and I'll show some examples of that, but it's still limited. All right, so with a group of people at Caltech, MIT, JPL, we started Klima. It's about 50 scientists, applied mathematicians, engineers, a lot of students involved. And we started building a new climate model. The idea was that we want to use data much more extensively than climate models have done before. But there are at least three challenges that are of enormous importance in climate model, and they may sound simple, but I think reflecting on them and taking them seriously is extremely important. Number one, climate is the quintessential out of distribution generalization problem. We don't have data for the future. The future lies out of the distribution of the present in many ways. And we need methods, we need tools that allow us to generalize out of the distribution of the observed climate. We want what we do to be used for practical purposes, for engineering purposes, for example, and ultimately also to advance the science. So in weather prediction, you can build a black box weather prediction model. You can test it every day. If your forecasts are bad from day to day, then you don't trust it. If they're good day to day, you trust it. You have day-to-day verifiability. We don't have that in climate. You need trust in models, and that to me means they need to be interpretable. You need to be able to have a chain of causes and effects that you can trace through the model and tell some causal story, at least, of how an effect, extreme rainfall in India, comes about by global warming. That's different in weather prediction. I think interpretability really isn't that important there, but it is hugely important in a climate context. And ultimately, we need uncertainty quantification. And that's, again, the issue that you want climate predictions to be used for engineering purposes, and you want not just point estimates, but risk estimates coming with uncertainty quantification. So these three requirements are important and were non-negotiable for us from the outset. And if you think about the success of what you might call reductionist science and deep learning, what it boils down to, the success of deep learning in many ways boils down to over-parameterization. It leads to very expressive models that have been enormously successful in many fields. However, it leads to very data-hungry methods, and it makes generalizability, interpretability, and uncertainty quantification challenging. Basically operating outside the realm of traditional statistics, where the number of parameters exceeds the sample size, UQ and the like, is not impossible, but is challenging. And if you want to boil down the success of reductionist science a la Newton to one word, I would call it parametric sparsity. It leads to generalizable, interpretable laws, such as Newton's law of universal gravitation. It's a one-parameter law that describes how planets orbit stars and how apples fall from trees and everything in between. Extremely generalizable, interpretable, straightforward to do uncertainty quantification, but it clearly reaches its limits in complex systems, such as the Earth system. It would be nice to have some equivalent of Newton's laws for, say, the reflectivity of clouds, given their environmental conditions. Many have tried, me included, to come up with such laws, but in systems as complex as a cloud or even the whole Earth system, that reductionist approach reaches its limits. So our approach was to say, well, let's combine the best of both worlds and be flexible and about where you use data-driven methods and where you use first principles and combine them in the best possible way. So what we did is we built an all-new climate model. It has an ocean model, atmosphere model, it has a land model, it has a land biosphere model, and the like. And we wrapped around that model a set of data assimilation, machine learning tools that can inform right now the model components individually. We're at the stage where we have a model and we train the model components individually with data. Eventually, and eventually is within the next year, we want to train the entire model jointly with data in order, for example, to be able to quantify compensating errors among model components, correlated parameters, and the like. Data for us is observational data. It's the gold standard, but also computationally generated data, such as large eddy simulations of clouds or ocean turbulence and sea ice as well. So we're building on domain-specific knowledge, the idea being that it reduces data demands and helps ensure generalizability of the models. We are leveraging accelerators, GPUs, to enable high-resolution simulations, both for global models, I show you some examples, but then also for these embedded high-resolution simulations that we use to pre-train ML components. And we build tools to harness diverse data, observational data, computationally generated data, for calibration and uncertainty quantification. And I'll say a bit more about how we do this. So Climate versus weather. When you predict weather, you want to predict the state of the atmosphere X hours ahead of time. It is what Lorentz called a prediction of the first kind. You're given the initial state, what is the state of the system a little bit later. Climate is different. Climate prediction is what Lorentz called the prediction of the second kind, where you want to predict how statistics of the system change given changes in boundary conditions. That's the name of the game in climate prediction, and that's the crucial thing that makes the climate problem different from weather prediction. So ML models have been very successful in weather prediction and predictions of the first kind. We have abundant data. You can do this with black box models, but the same approach cannot work in the same way in the climate problem. The problem is very different because you want us to predict essentially infinite time statistics of the system. So from the outset, we said we need to learn not from states of the system, the trajectory of states, weather states, but from the climate statistics. It has a number of advantages to take that point of view. Climate statistics are very smooth in space and time. So if you take cloud cover, you average it in time. It's a spatially smooth statistic, whereas the cloud states, of course, are spatially rough, whereas the clouds in one place or another, it looks very different. The statistics can include any number of things that you think are relevant for what you want to predict. For example, high order moments of the precipitation distribution, monsoon rainfall extremes could be a statistic you would want to predict, and you could put in a loss function. If you take that point of view, then learning about the model, machine learning, is no longer a supervised learning problem. You're not learning direct input-output maps, but you're using the statistics of the system in an inverse problem setting to learn about model components. And that is our approach. It has some disadvantages, one of them being that the loss function evaluation is very expensive because you need to accumulate averages of the loss function over some time to accumulate the loss function. So not just 6 or 12 hours or a few days predictions, but decadal averages. Bit more formally how we do this. So we want to learn from diverse data and from diverse statistics of data. So we have a loss function that looks schematically like this. Y is some climate statistic, the angle brackets indicating a time average, for example, over a season or several seasons. G is a climate model that maps parameters, data, lambda, nu. These are various types of model parameters, physical parameters, parameters of machine learning models, lambda or resolution parameters, maps those to climate model output, temperature, winds, and the like. And then there's an observation operator H that maps the climate model output to the statistics we actually observe. And we minimize some loss that is reasonably an L2 loss, reasonably because we are looking at time aggregate statistics. There's a central limit theorem applying that says that these statistics are reasonably Gaussian, and it makes sense to use an L2 loss with some covariance matrix gamma here to minimize. So that's the loss function we have to minimize. We're ending up with an inverse problem that boils down to learning about parameters. Theta, nu, resolution can also be a parameter, lambda, from these climate statistics. It allows simultaneous learning about physical and machine learning parameters. It comes with the advantage that this approach ensures stable models because we're directly learning from statistics, meaning the model needs to produce these statistics, long-run statistics, meaning that it will be stable for long rollouts. But no free lunch. The loss function evaluation is expensive, and you cannot use off-the-shelf machine learning, supervised learning methods to minimize this loss function. The algorithm we came up with that is our workhorse for solving these inverse problems, we call calibrate, emulate, sample. It consists of these 3 steps: calibrate, emulate, sample. So we have a map from parameters theta to climate model climate statistics Y. And that map is our climate model. And the goal is to learn the distribution of parameters given these statistics. And we do this in 3 steps. In the first step, we use derivative-free methods, ensemble Kalman methods, to get the first estimate, if you wish, of the parameters theta. Or perhaps a better view of what this first step consists of is find pairs in a potentially high-dimensional parameter space theta, pairs of parameters and model output that are well placed somewhere near the posterior maximum of the parameters in theta. We use various forms of ensemble Kalman methods. We continue to develop more of them. They have several nice properties. They have a smoothing property that for noisy statistics, they don't tend to get stuck in noise-induced minima. They're derivative-free, which is nice because you can use them as very complex models where the derivatives may be complicated to evaluate or may not even exist because they're, for example, they're phase transitions of water, they're discontinuous. And they're scaling very well to high-dimensional spaces. They're used in weather forecasting for billion-dimensional optimization problems. So we know they scale well to high-dimensional spaces. They're very efficient at finding good points in high-dimensional parameter space. You can view them as solving an experimental design problem in a high-dimensional space of finding good points in this parameter space near the posterior maximum. So they're based on ensembles of climate model runs, typically order 100 or so. You need to iterate them a few times, 5, 10 times or something. And in total, you get something like 500 to 1,000 climate model forward evaluations out of it. And that allows you basically get 500 to 1,000 pairs of parameters theta and statistics y. It allows you to train emulators on these pairs of theta and y's. And the emulator can be Gaussian process neural network. We've now experimented with higher dimensional generalization, random feature models, and the like. We train an emulator of the parameter to data map, and then we can sample from this emulator, and the sampling becomes very cheap. We can use MCMC because the emulator is very fast to evaluate. And the upshot of this calibrate emulate sample algorithm is that we can do essentially Bayesian inversion with something like a factor 1,000 speed up relative to standard methods like MCMC, because the computationally expensive step is the calibration step, the forward model evaluation. That requires only 500 to 1,000 forward model evaluations rather than 10 to the 5 or 10 to the 6 that you would need with MCMC. So let me just show you some examples of where all of this leads to and what we have so far. So here's an example of a model of stratocumulus clouds in this case, or it's really a general cloud model, and the example that shows stratocumulus clouds. In blue is cloud fraction from a high-resolution large eddy simulation. In gray is a typical climate model, a good typical climate model. They all underestimate cloud cover by factor 2 or so. In red is our new model. This is a 1D model, several PDEs, and I'll sketch out what this looks like. That captures these stratocumulus clouds very well. And it captures really all clouds very well. This is stratocumulus. Here is a comparison with field data. Excuse me. And this 1D model embedded in a climate model is something like a factor of 10 to the 8 faster than a direct simulation with a large eddy. There's a large eddy simulation. This is now embedded in a climate model. Sorry, I've got a bit of a cold, but I'll get through this. Just to say a word about what this model looks like and how we combine physics here with machine learning. This model is coarse-grained Navier-Stokes equation, rigorously coarse-grained. There's a continuity equation here, a tracer equation. And once you coarse-grain, you end up with terms on the right-hand side that require closure. Turbulent transport terms, we coarse-grain in a conditional way over coherent structures and more isotropic turbulence. Then there's mass exchange between coherent structures and isotropic turbulence, entrainment, detrainment. The point is on the right-hand side, there are a bunch of functions that a priori we don't know what they are, and we can't get from first principles. And these functions are great targets for machine learning. What we did for the example I showed you is we created a large library. This is 500 or so large eddy simulations, mostly over the Pacific, but by now it's spanning the globe. With which we pre-trained this model. And what may be of interest to some of you, there's a lot more of these simulations coming. There's a collaboration with Google. There are thousands of these large eddy simulations of clouds soon going to be available to all of you to train models on. We trained the models on There's a question, Sagar.
Yeah, so when you're talking about the stratocolumnus and the cirrus, can one do something similar for even lower lying clouds like nemocolumnus, the ones which are doing it for rain, because they would be even more chaotic,
Yeah.
so to say.
Yeah,
I
you
mean,
can
just
do
from a
that.
mathematical perspective.
Yeah, you can. So yeah, there's nothing special about Cumulus Cumulus here. It's just this is the biggest uncertainty. You did this first, but you can do this for
Okay,
any type of cloud. And these large eddy simulations, what we did is we drive them with output from climate models, from various climate models actually.
okay.
In the present climate, in warmer climates, and you can do it in any place on Earth, any season, however you like.
And in general, how many different parameters would this sort of a simulation use? I mean, what is the
Um, yeah.
dimensionality that we're looking at here?
Yeah, I can tell you precisely. So here's an example. What we did is we trained the models here on the present day climate, and then we checked that they still are good in warmer simulated climates. And here are just two examples. What we do is we have these functions on the right-hand side. We reduce them to non-dimensional functions of non-dimensional groups.
Okay.
And turns out there are 6 non-dimensional groups that matter for this particular entrainment closure. And then we tried various things. We started out with kind of guessing physical functions as this Cohen et al. Reference. That already was a big advance over the state of the art. But then we used these data-driven approaches, and here's one linear regression model and one Waldwisch-Scheller neural network. So the linear regression model has 6 parameters. In this particular case, the neural network has order 200, so I'm not quite sure what the exact number. It's relatively shallow,
Okay.
but if it turns out the linear regression model in this case is just as good as a neural network.
Oh,
It's not always the case, but here it's nice to see that we're just doing fine with linear regression. In either case, we saw something like a factor 3 error reduction, in this case in cloud liquid water. The left is training with present date climate, the right is validation with a 4 Kelvin warmer climate. And the nice thing is that the validation error decreases in just the same way as the training error, meaning this generalizes extremely well. And that was very, very reassuring. And I think the strong generalizability comes from taking the physics extremely seriously in this. I mean, in the end, the training of the data-driven part, I mean, clearly it helped and gave us a significant error reduction, but that this generalizes well is due to taking physics very seriously.
got it. Thank you.
Yeah, thanks for asking, by the way. Few other highlights. So I mean, it's an all new climate model, and it was a daunting thing to begin with, to start with nothing and build something. But by now there's something that's kind of fun. So here is computational performance of the atmosphere model. This is relatively hot off the press. We got some compute allocation at the National Center for Atmospheric Research in Boulder in the US on their GPU supercomputer, and we were able to scale our model and see how well it does. And the nice thing, it shows very good, strong scaling up to the point that there simply is not enough arithmetic intensity per GPU. Once you reach number of GPUs becomes too large for a given resolution. Up to that point, it scales extremely well, strongly. And the thing that's nice, so the vertical axis is simulated years per day, the horizontal axis number of GPUs. When you run climate models, you want to be somewhere in the realm of more than 1 simulated years per day, so you can iterate and you get a few years of throughput in a few days. And the nice thing is, so we achieve, for example, 1 simulated year per day at 55-kilometer resolution. That would be considered a high-resolution climate model on just 4 GPUs, for A100 GPUs. Or if you have more GPUs, H100, it's about a factor 2 faster on the H100s. The critical point is we can do climate simulations now at a few tens of kilometers resolution, which would be considered high resolution, with a modest number of GPUs. It doesn't require a huge supercomputer. I mean, it's something that anyone can get access to. And the code is very modular, extensible, easy to experiment with, and our hope is that you and others will use it and can use it and experiment with it. The performance of our model is on par with the DOE C3SM, which just won the Gordon Bell Prize for their computational performance. It's producing global climate simulations. Here are just some examples. Precipitation, water vapor, zonal winds. For climate experts, if you stare at this long enough, and if I would leave this up there for you long enough, you see there are still problems in the model. But the important part is we have global simulations, we can iterate on them and improve them. It has a land model. The land model, likewise, it's all GPU native, modular. It's a soil hydrology model. It's a biophysics model. The biophysics model is built to take modern data on board immediately. Modern data include data such as solar-induced fluorescence, data for evapotranspiration, with which you have calibrated the model. It has various data-driven components. And to give you just one example, for the clouds, there's a very strong physics component. There are just 8 additional PDEs governing what cloud does. But what clouds do. But here's one example: snow thickness. Here's one equation for snow thickness. It's an ODE. To the right-hand side is a neural network. Snow, of course, is a physical system, but it's very complex. And the physical models that we have, we don't have the same degree of trust in them that we would have, say, in a large eddy simulation of clouds. And here we went entirely data-driven, and that actually worked extremely well. It's work from a student, Andy Charbonneau. Just learn an equation for snow thickness, given various inputs that matter: snow water equivalent, the previous snow thickness, atmospheric temperature, relative humidity, and the like. And we trained it on SNOWTEL data, that's snow data for the US. And then we validated in various other parts of the world. Here's an example from Austria, for example, a seasonal cycle where this machine learned model for snow thickness does extremely well. And it's a very simple model, but this is a bit more complex neural network. It achieves roughly 30% error reduction relative to state-of-the-art snow models. And there's a linear regression for comparison here, and here the linear regression doesn't do all that well. The neural network clearly beats the linear regression. Our partners at MIT develop an ocean model. It's by far, roughly factor 10, the fastest ocean model around. Likewise, it's GPU native, so you achieve, for example, 10 simulated years per day on 64 A100s at 1/12 of a degree resolution. That's significant because what is weather for the ocean are eddies of scales of 10 kilometers or so. And this has been a big problem in ocean modeling, that they needed to be parameterized, all these 10 kilometer eddies. Now we can resolve these eddies with modest computational power. Computational power you can get on the cloud, for example, something at 64 A100s, and achieve a throughput that allows you to iterate 10 simulated years per day. So this was a breakthrough, and that it makes this mesoscale prioritization problem somewhat unnecessary. And it was a surprise to us too. When we started the project, we did not think this type of computational performance would be achievable, but it is. And I think a good part of why it was achievable was building all new code from scratch. That's from the outset optimized, for example, for GPUs. And there's also a lot of work going into numerical methods and the like. Our software it's written in Julia. It's a very expressive language. So up there on the right, you see this is an actual piece of code from our atmosphere model. It's the continuity equation and the momentum equation. It's just coded in a way that makes it a pleasure to read. Of course, underneath there's a lot of machinery to make this performant and make the discretizations good on the sphere and the like. But it's written in a way that makes experimentation relatively easy. You can plug in your machine learning components here without too much trouble, things that's really hard to do in a Fortran model, for example. And it's fast. I mean, here's just one example of GPU versus CPU performance. There's a factor of several hundred difference. So far, this was all about the climate modeling part, how to get from data to climate models and get better predictions. And so we're in the process of putting these model components together, and we'll have predictions in the coming year, global climate predictions. But there's a second part. How do you make predictions useful for people and usable? And writing IPCC reports is good, but clearly not very helpful for planners. To give them a 4,000-page report on all sorts of climate changes makes it hard to plan infrastructure. So you need a bit more. And I think there is, what may be of interest to all of you, huge opportunities for AI on that downstream end of the value chain. Adaptation has enormous cost benefit has enormous benefit cost ratios. Maybe don't need to belabor the point, but there's this the Global Commission on Adaptation estimated that the benefit cost ratio of various adaptation measures ranges somewhere from 3:1 to 13:1. And included in that is strengthening early warning systems, predicting risks of floods, for example, and making infrastructure resilient and the like. And what you need to harness this potential is assessments of climate risks on scales of kilometers. That's where impacts happen. Say you want to right-size dams, and they might have catchments of 10 kilometers squared or so. So you need to have good estimates of precipitation, of high precipitation probabilities, the probabilities of high precipitation occurring on scales of kilometers. And running climate models of kilometer resolution is still prohibitive. The problem again is that even if you don't refine the vertical, from going from 10 to 1 kilometer is a factor 1,000 in compute, and 10 kilometers or so we can do. But our take is, rather than using an extra factor 1,000 in compute to go to 1 kilometer, we should rather generate ensembles of size 1,000 that allow us to assess risk and explore climate risks broadly. Then how do you get to kilometer? Well, you can embed high resolution models, but I think the big opportunity here is using generative AI tools to downscale to kilometer scales. And here's just one early example of work that was done in my group. This particular example uses generative adversarial networks. Since then, we've published papers on using diffusion models for the same purpose. The key here is this: we had high resolution models for training, or high resolution weather data for training. Then we have standard low resolution climate models, say, and this is just an example from an idealized turbulent flow with precipitation in it. And on the right, you see an AI-generated super resolution. So what was done here in this particular case, training again on unpaired data of low resolution and high resolution. So they're not matching frame by frame, but what you want is to condition a prediction of high resolution and low resolution output such that the prediction reproduces the statistics of the high resolution output. And this here works extremely well. I mean, you can stare at the right. It's basically an infilled version of the middle panel with all the details filled in. And you can examine this in more detail. For example, rare event statistics are very well captured in a way that in this particular case is very computationally efficient. So the generative high resolution model is something like a factor 500 faster than the actual high resolution model we use for training. And trying to do this now with actual weather data and not with this type of model, but with a diffusion model, for example, for rainfall in California. I think a lot more of this type of work can be done and should be done, and this is very fruitful for studying climate impacts. So the goal for us, and I would say for the climate science community, should be that we provide platforms for actionable climate information. On the back end, there should be climate models. Perhaps right now of resolution around of tens of kilometers, you can produce fine-grained projections from them with, for example, generative AI models that allow you to assess risks of extremes and the like, the things that matter for planning, that matter for human impacts. And ideally, I would like those risks to be converted into information people can use. For example, if you're an architect designing a building and want that building to be comfortable 20 years from now, I would want you to have access to the information you need to design the building such that occupants are comfortable in it a few decades from now, and that you have access to the climate data, the climate projections a few decades from now that you need for that purpose. And same goes for other applications. There should be an ecosystem of apps really that meet stakeholders where they are in their decision workflows. Let me just wrap it up here. So where we are, we have built atmosphere, land, ocean models. We have seen something like a factor 3 error reduction for in crucial small scales in the atmosphere and ocean. We're not done yet. Let's see how much better we can get it. We have shown how you can do machine learning from noisy and heterogeneous statistical data in an inverse problem setting. So these entrainment functions that are showed, they were neural networks, but they learned in an inverse problem setting with ensemble Kalman methods, not through supervised learning, without derivatives. And the key was here to essentially do derivative-free Bayesian learning roughly a factor 1,000 faster than standard MCMC type methods would give you by accelerating it with machine learning. We have performance portable, scalable atmosphere, ocean, land, now a simple sea ice model too. What remains to be done for the rest of the year for us? We want to demonstrate the first climate model that harnesses terabytes of Earth observations. So we are in the process of doing that. We have pre-trained the model with simulated data, and now if you want to use machine learning terminology, we will be fine-tuning it with observational data in the coming months. And our goal is to demonstrate at least a factor 2 error reduction in key global metrics like RMS errors and precipitation and the like. We want to provide the first climate predictions with observationally quantified uncertainties. So there will be some spread in the predictions, but quantified on the basis of observations. And we want to make these models to be usable, accessible to all. So the code is already public. It's GPU native. That makes it already much easier for people to run it on their machines. We want it to be cloud accessible eventually as a tool for the research community and eventually also for the planning community. So I'll leave it with that. We should maybe say a word of thanks to our funders, Schmidt Sciences, National Science Foundations, the Office of Naval Research, Cisco Foundation, and in the past, various others have provided funding for this type of work. So thank you very much, and I'm happy to answer more questions.
Thank you, Tapio. Can you hear me?
Yeah.
Okay, thank you. This was a wonderful talk. Great achievements and very ambitious goals to work towards. I throw that open for questions. Questions can be, I guess, online, maybe clearer, so maybe we can go with those. Sagar, you want to go ahead?
Yes, so I had a question, but before that, I would also like to just say, Professor Schneider, this was a very amazing talk. Thank you for that. Hello.
Go ahead.
Good.
Yeah, so my question is regarding this whole idea about being able to look at how climate change is happening. So if we are looking at the amount of carbon dioxide which is there, I mean, one of the major proponents would be CO2 in the atmosphere, but along with that, we also have to look at the amount of CO2 which is there in the oceans, because oceans are having the major share of CO2, right? So when we are looking at this whole model which you are looking at, most of them would not be considering the marine ecosystems which are there, which would be helping in sequestering carbon, specifically with regards to how ocean currents are going around. Because whenever, let's just say, I'm having algal bloom or something like that, that by itself would be sequestering carbon at a much rapid pace compared to how any other process is doing that. So, I mean, are the current models that we are working with, specifically the types which you are referring to over here, they're taking that sort of a scenario into consideration as well?
So right now we don't have a full ocean carbon cycle yet, but we have people working on ocean biogeochemistry. The ocean carbon cycle, there are actually two types of problems. One is simply the physical mixing in the ocean that mixes carbon from the surface ocean deep down. That's a big problem in current models, and you can see it's a big problem, for example, by looking at their mixed layer depth that it has large biases. So the physical problem we, especially my friends and colleagues at MIT, have made a great deal of progress on. And we're just starting to build an ocean carbon cycle model that has sort of the dynamics of phytoplankton, zooplankton, nutrients, and the like. That's work in progress. It will be a while before that's online. And I hope then we can make more meaningful statements about carbon sequestration in the ocean as well.
Thank you.
I see there were some questions in the chat I can maybe start to answer. So how do you verify and evaluate the quality of computationally generated data? Yes. So our workflow is roughly as follows. These large eddy simulations that I showed you, we usually do them first as we develop model at sites where we have good field data, typically aircraft data. And we validate the model against the aircraft data and spent a great deal of time on numerics and the like to make sure that that reproduces the aircraft data well. Of course, even in large eddy simulations, you still have to deal with microphysics, processes on micrometer scales, droplet formation, and the like. Those remain parameterized and remain somewhat uncertain. Second question, what are the challenges in using the ensembles? How many to select? How to combine the results from various models in the ensemble? Not quite sure what the question refers to. So the way we use ensembles is we use them in ensemble common inversion. The ensemble in some ways represents discrete approximations of derivatives, somewhat like in stochastic gradient descent. The ensemble size depends on the specific method you use. There are some methods where the ensemble size is of the order of the number of parameters. The key, though, is that these methods scale to high-dimensional parameter spaces without needing huge ensembles. And the trick for making that work is something called covariance localization. So there are localization methods. There are covariance matrices you need to invert along the way. They need to be regularized, and there are ways to do that through localization methods that eventually allow you to say weather forecasting use ensemble size 100 to estimate a billion parameters. How interpretable are these models compared to regular ML black box models, and what more can be done to increase interpretability? That's really important to me. We put the machine learning components on the level of processes where you can relatively directly verify and test them. For example, for turbulent mixing between clouds and their environment, we can relatively directly test the models against large eddy simulations. We can interpret them relatively well. For example, for entrainment, there are in the end 6 non-dimensional groups that matter, so 6 input features. You can make plots and you just plot the functions here. And that's how we interpret them. We look at them and said, okay, this makes some sense. It's not what I would have guessed, but I can make some sense of why this function looks that way. I think that's important in a climate setting, because if you would try to learn holistically a whole bunch of processes in one go, you immediately forego this opportunity to probe processes piece by piece with selected experiments, for example, in laboratories and the like. And it becomes much more of a black box and much harder to trust. I think for us, it was important that we can probe every component, at least in principle, even if right now we don't have the data. If there's a machine learned model, say for microphysics that we use, that gives us a certain relation between, say, properties of ice nucleating particles and how ice actually forms in a cloud. Even if we don't have the data right now, this is in principle measurable in, say, a cloud chamber in the laboratory and can be probed and tested that way.
There's a comment by Sapta Rishi in the chat box. Yeah. All right, then I just have a quick comment. You showed some use of generative AI. I think it was in the many simulations. So you had, I guess, a coarser timing model. You had some kind of a more finer, maybe actual data. I'm not quite sure. My question was, it looks a bit like multi-level Monte Carlo simulation or multi-level technique used in PDEs, ODEs. Can one relate that in some way, where you have these coarser level realizations and somehow you use them to build a much more refined version? Thank you.
Okay, the sound is really terrible from the room, so I need to try to do some interpolation. If someone else online really understood the question, better help me out, maybe in the chat. So was the question about the generative models in the end for downscaling, and are they multi-level models or something like that?
That's right. So in this generative AI downscaling, is there an analogy to multi-level simulation multi-level, OT simulation?
Yeah. So I should say, I mean, the example I showed you from the GANs, we're not actually using anymore because we have better models now. I think the approach we actually are taking, and others are taking too, is, for example, groups at Google that are doing similar work, are building on diffusion models. And there are different types of diffusion models that people use for that purpose. Multi-level models, in that particular case, no. They have a place in many other cases. For example, for precipitation, an issue is that most of the time it doesn't rain. And then it makes sense to use multi-level models for modeling when it rains and how much it rains separately, for example.
Sagar, you have one more question? Go ahead.
I had another question. I was asking this to Sandeep as well yesterday. So when we are doing modeling for something which is chaotic, like how you were looking at diffusion modeling over there, uh, how good can the result from AI be? Because I mean, like if I'm looking at something which is coming as a solution from Navier-Stokes, which would be having some sort of a turbulence involved, then I mean, what sorts of results can we expect over there in the modeling?
Yeah, I mean, this is a good question, and it is the reason why A, we focus on statistics in a loss function, and B, we use these ensemble Kalman methods. So if we're dealing with a chaotic system, right, it's very noisy. Statistics are still noisy. So that means if you would use gradient-based methods, you have very noisy gradients, and it becomes very easy to get stuck in noise-induced minima. For long rollouts, you have problems with vanishing gradients and the like. So statistics A are smoother, but well, they're still noisy. And these ensemble methods we use, they have nice smoothing properties, which you can understand from mean field approximations, how they arise, that largely avoid the problems you would have with gradient-based methods. So I think there's a case to be made, and it's something we're looking at and studying in a bit more detail, that these gradient-free methods could actually be advantageous in these noisy systems, even if you can differentiate them just because of those smoothing properties.
Okay. Thank you.
Thank you, Tapio. We already taken too much of your time. But really appreciate your staying up and giving this wonderful talk. This was the first event we had for the Center for Data Learning and Distance Sciences. And you will also know that Tapio is one of our mentors, and he's been very helpful in giving direction to various activities we are doing on this topic.
Yeah. Thanks for having me, and Godspeed for the center to take off. I'm looking forward to seeing what comes of it.
And we look forward to seeing you in India soon. Thank
Yeah.
you.
Thanks.
So we can maybe meet at 10:55. We can quickly run the 5 minutes. We can get some tea and coffee outside. Part of dictated by this. Right. No, no, but for then can you really clear that that is, like, but is that how you, is that what you think? How do you make it? Texting that is targeted for texting and telling you what you are saying to the model model. Then all could understand that you how to. Yeah, so if that will work that. Oh, but then what is logic with
Did you load your you got your pen drive?
Yeah, I loaded.
how do you inherently make that model also? Like, is that something I'm sorry, I will get. Then do it now. Mic check one. Hello. 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 Hello, mic check one, two. Mic check one. Hello. Hello.
एक मिनट से कर यहाँ से कम कर देती हूँ कि मैं वहां से बढ़ा
वो representative hello. 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 Mic check one, two. Hello. Hello. Online is good.
People.
For online, I think the remaining event is going to be physical, so if you're nearby, I'd encourage you to just come by to the hall. The food seems to be surprisingly good here. Okay, we'll start the proceedings. I just again mention that, this was the first event that we had for this center to give us we will start the journey. This center, we do, yes, here. We're working on basically data science and AI and network. Some of our focus areas are weather and climate modeling, and some of weather modeling is nurturing the new area for us. Area also is financial modeling at the intersection of financial modeling and AI, epidemiological modeling, reinforcement learning. These all have kind of common themes and techniques. So as we go, I'll request our Vice Chancellor to say a few words. That's it. Makes no sense to have a welcome address. But I wasn't here yesterday, so I'm full start of the day is fantastic. And also, congratulations for starting off. The activity of the center with such a bang. It's very interesting for me personally to end where I can speaking. Partly because I myself in my work quite a lot on mathematical techniques in astrophysics, my field. And I can see previous interaction with the institute in Pune. That's the work that's being presented here. The obvious parallels between what we do in simulations, large scale simulations, astrophysics, and simulations here. And in whether or not someone. And the camera. So it's very interesting to see the parallels between this lot to learn. And as Sandeep said, the point of the center is to look at the methodology that's common between it's been done by virtual finance and epidemiology and climate. And so astrophysics is actually very much in the middle. Couple of interests for me particularly here are as follows. For example, again, drawing parallels to astrophysics, which I do. If you do a big simulation of a large system, and that's basically talking about the whole universe, so the resolution of the grid is going to be of the scale of just about a galaxy. So at different scales, the physics that's important, very different. And so already in astro topology simulation, what we do is to use MI techniques to deal with a lot of the subgrid problems, to look at how data is integrated into physics that comes in shorter scales, and look at how that relates to it. I can see that that's happening here also in very spectacular way. And that's a very interesting concern, and I think we can all learn about it. Because even though the details of the physics might be slightly different, actually the way the integration of the data is handled on these various scales and how computation is sped up, this is very important. Most of the thought is going into how to speed up. Second thing is I've been personally interested in is to look at how error propagates, measurement error propagates from the data into the training sets, into the use of the primary data. The physicists, we worry a lot, much more than computer scientists do, on measurement error. And then in the end, in the prediction, in the range of uncertainty, how that is characterized. And that's very interesting. Here, it's wonderful to hear Tapio talk about that too. And also, I'm very interested in outcomes and uncertainties. That's, I think, of course, in the financial world, another huge issue. So, wonderful to start with this work of the center, truly interdisciplinary approach. Of course, it's very important here. Thank you very much for that. And I look forward to the rest. Thank you. Okay, I'm going to request Rajivan now to get the next session. This is our next speaker.
Thank you, Sandeep. So the next presentation is will be done by Dinamini. Dinamini is the senior scientist at India Meteor Department at Delhi. He joined IIT in 1993. So because into BSc. He's basically a PhD in mathematics. Now he's heading the forecasting division at main forecasting division of another work on understanding and source, etc. So the denominator is
I should add that this is workshop is jointly organized with Professor Rajivan and from the Pata Specific Special Working Group is coming in.
yeah, good morning.
Post-match. So,
So very good morning and thank you, our Rajivan sir actually. So we have worked right from beginning. I was in Pune and then Delhi. So I will be speaking, for which, this workshop is that, you know that ultimately the any models or anything you develop, it is for the utility of services actually. So I will not, touch any, poor part of AIML. Let me very honest, but I will try to excite you about the current status in the services we do, whether it is the weather or climate, something, may fascinate you. So that is my hope. So this is my topic. I was trying to, get you all into the topic actually, which can help you so that you'll more excited to work on this. So that is the, current trend, that is multi-hazard early warning system. So that means multi-hazard early warning means, as you know, that you can take anything like heavy rainfall, or what inundation, flash flood. Inundation means water remaining from the period. Okay, so that itself, characteristics of an event. And then flash flood, takes everything, anything on its way. Again, depends on where it is. Urban flash flood. If it is hills, it is something like, followed by landslide, multiple. So that land, heavy rainfall over hills or over a city in itself be multi-hazard itself and triggered by the heavy rainfall. So how you can, deal with that particular, multi-hazard early warning system. And extreme weather event, as you know that when you talk about climate change, any driving force, global warming or anything for the climate change, but that puts you the extreme weather event. So basically, I will be, offering over weather, hazard, and impact model. So weather model is one part, but what about the hazard or impact to particular, particular area of exposure? And as you know that these days we are talking about automation, DSS, something like this, and support system end to end. So twin digital system, weather climate end to end, or something like from climate to weather to different industry like agriculture or to power sector or to marine. Okay, so ultimately the early warning system what you need actually. So if you have an effective early warning system, it must address the extremes actually. I mean your system should capture something like 100 centimeter, 1000 millimeter of rainfall in 24 hours or something like Himachal Pradesh, what is happening or something recently we have in Gujarat, some 5 days, 7 days, that scale. So try to define the subject actually to, where are the things. Impact-based forecast, as you know that these days nobody talks about only weather forecast, but you give something like in terms of what it will, cause actually by such weather. Okay. So actually this will, I know. Yeah. So here. Yeah.
So on the stage.
Yeah. So this is very interesting. I'm not defining the. Yeah. So here. So I am not defining the basic, but what I try to bring here is actually whether I don't know the instant of a parameter of the atmosphere. So what we are more about the weather using time, whether using time, like rainy, cloudy day, fog day, okay, something like day having the temperature remain 40 plus, say from 11 a.m. to 7 p.m., something like that of the weather. And when you find the similar in the climate scale, actually, it's not only the temperature average, something like how many days you have a 40 plus temperature. So that is really worrying, because that put extra pressure on all the exposure. So you can say like in Delhi, you have 40 degrees say from 10:30 to 9 p.m. That kind of parameter. And you know that the weather can be like you have come out of your room. So weather makes that particular dress, asset or umbrella you carry. So when you talk about climate, it is a whole scale where you are living, your house, your transport, something like that in that. So the extremes, when you talk about the extreme, not only the actual temperature of a day of the weather, but what is the rainfall intensity for hours or for 10 minutes, something like that, because that suggests the trigger the intervention, like for landslide, the rain speed or rain rate is very high or very high impact, something like scale period or period. So as we know that as the global warming and climate change they are affecting the extreme, also the range and vulnerability, because you could see the kind of growth in the urban pockets or hill area. So because of the increase, the value of the duration of the event, so that is high risk of high risk. So we actually regularly experience the intense cyclone or long period tail of heavy rainfall, and also their hazards and the impact they are. So that is the kind of impact. And another thing is that that already you have today the day two I just seen our lecture that the number of rainfall is high intense rainfall is there. So what you are getting like this graph shows, like in 1990. In 1900 something, you are getting a return period of 15, but in recent you see you are getting a return period of similar rainfall like Mumbai crossing 400 million or Chennai crossing 600. You are getting typically in 10 years or 20 years. We are getting earlier in 50 years. That would say extra effort. So when you come about the whole this chain, what you see all the different kind of, whether it is heavy or something like tropical cyclone, or they are figuring the different hazard, that is also increasing. It's very good to to play all this video, wherever it comes, it gives you what is the global climate change or global warming, how it is triggering different kinds of extreme weather with respect to what is temperature rise or many other parameters they are lacking in this. So you can see because of this repeated occurrence of the extreme weather event, the risk has been almost 50% or 40% increase. This is ideal case, an ideal case, but smooth area like any region like Himachal Pradesh, there may be much higher. So see the impact of this global warming or single thing like increase in temperature. It is one of the impact. What I want to tell that the most, the most impact among the all kind of weather events, whether you take the rainfall event or take tropical cyclone or take a snowfall event or anything you take, understand? So the highest vulnerability or highest impact is the temperature. That is the heat wave or cold wave. So getting a day, having high temperature or getting a heat wave spell very longer period, there is a tough most in the impact of it. So when you talk about extreme weather event, you must be in your highest preparation to handle the temperature related. So that is the and second it comes actually the rainfall. Too much dry for prolonged period or too much very high rainfall for prolonged period, like we get also every month. And as you know that whatever average you are getting in the weather events, severe weather events, too much cold or too hot, because of the increase of the temperature or impact of the climate change, your becoming more prominent, more active. So always the very high come. This year is the fourth highest or fifth highest in last 150 years. So that means the highest is more biased in the late 2000. So that is the summary. Not only that, but also the daily extremes in terms of the rainfall events, in terms of the temperature, or even if you take the spell period, they are much longer and much intense in region. Actually, I provide, as you know, that it's present in the almost in all service sectors, not only the public service, the key sector is the disaster management. Actually, helping giving an effective value by monitoring the events and giving time to time something like weather forecast, warning, or something likely condition usually generate over a location, different temporal scale. But it also, gives all these services like aviation or something like agriculture, shipping, all sectors are present are there within our energy and also marine. You can see in marine also various plants is there, for fishing and other things. And then these are the some other things. So I work in the National Weather Forecasting Center, and we are doing all different work. So where we are exactly working, as you talk about, I was telling that mainly our focus area, the multi-hazard early warning system, and try to basically develop from college, but in a more, terminology, with what I keep finding here. Very
Generally, these alerts that we get for heavy rainfall from IMD
Yeah.
to the alert, what information do you use to arrive at that?
That only I will actually know how we generate where we. So if we talk about the alert and warning for any kind of related to any severe weather event, so that to proceed in that direction, so we have implemented something like not only the weather forecast monitoring, but also we generate kind of impact or something like what kind of impact it will cause, whether it will close the road or the area, something like that. So for that, these are the different components we have worked at, like a hazard or impact or specific events. And finding the risk and vulnerability. And then that monitoring system is very much needed to generate any kind of alert or warning. Because the current status we have to detect or decide. Then I'll come directly to the multi-hazard early warning. I know that what is multi-hazard early warning? Like I was talking that first and foremost that the area, like which area, it has more prone for heavy rainfall or heat wave. It is too much rain. And of course, all these regions very in this February. first and foremost, to develop any early warning system or generate any kind of, message, something like that. Have full knowledge about the different events and also what is the kind of thing scenario it depends on your data. So data are the main actually things where very important. So here not only work with the weather data, but here you work with the exposure data and what is different kind of activity also, like agriculture, transport, tourism, whatever in this domain. And second thing is to reach to any kind of real-time system actually in terms of say you want to develop any early warning system, you have a first pillar of this value chain is the risk analysis and then basically hazard means you have to take all kind of big parameters like weather, hazard, something like that. And then the second part of this is that you should have a good observation. And you should have a very say AWS or something like weather monitoring system, automatic weather. Of course, satellite radar, they will be adding to your monitor. And when you come to the analysis, so you should have a solid integrated platform where you can analyze all these data after receiving some clear sources. And second thing is that ultimately you go for. So in the forecast system, you have an array of methods. Like when you use NWP, you can use AIML, you can use pattern matching, or you can use what we call the synoptic or analysis, thing like that. And then ultimately, for whom you are doing, for the public or for your users or just a minute. So you should have a good system to communicate that this is the things happening right now and this is going to be or this is going to cause more rainfall or these temperatures like to given say for 10 days, 5 days, something like that. Then last is the, by using this information, different the service provider, they can act up. That is the preparedness and something like response, something like that. This is the, all these pillars we are working. We have a stakeholder as earlier as I was. We have a user group, then a different specific role. So if we talk developing the, the main thing is this. IND works upon mainly the observation, analysis, data, and also the weather prediction. So these actually different university and collaboration here. And this, as you know, communication it is part of government organization and also and this part, if we see, this is actually I can tell mainly community based. The preparedness or response. You are giving say something is coming severe weather. So this must be in the people setting. So if you see in this, you can see that anything you are developing early warning or multi-hazard early warning, so any component you are doing explain. So all of it to equally grow. Then only the system adjusts. So you can see in the globe that some country may have better monitoring system, but if it does not have a communication to the public or preparedness to just that is. And second thing is that you can see that development and partners. All these four components need strong partnership, and any research or any development from anywhere will equally, coordinated among the group. So this is you can see that anything if you are working on the say heavy rainfall, so it has different techniques and technology. You cannot take a heavy rainfall with a fog or a heavy rainfall with thunderstorm. When we were initially in the career, we see the rainfall map and we predict not like the monsoonal heavy rainfall and thunderstorm surging, severe weather like lightning, like strong wind. These are the different, they need different approach, different. So all should be different for specific event and specific object. So coming to the, the multi-hazard early warning system is something giving a scope actually, on which it can handle various hazard events or single hazard or maybe multiple hazard out of land, right? So the multi-hazard early warning system address the heavy rainfall early warning by considering all its components. So try to, this is very really the things you need talking about heavy rainfall early warning system. cannot, forget the impact it caused. Multi-hazard impact it caused. So that you have to take end-to-end actually, right? It is somewhere how the flow, how the network, or how it impacts the product, where it will come. So, and second part is that it should be efficient, actually integrated, and it should its purpose is to address that risk actually with the well prepared plan. So that is the you can see that two things coming up that every individual has the right to get an early better. You can talk about lighting, cooling unit, and say 1 hour. That's right. And that's the early warning for all actually. Try to send a WMO to even stop also register about how we can reduce the impact severe weather. Like that on periods, periods like agriculture or anything like coming to secondly, actually like various groups are living. Poor is there, old people are there, children is there, giving like over any plot. So how you can prioritize their rescue or they can be saved. Coming to the these are the different you can see the value chain like common alerting protocol. Communication remains like Malayan say about that. Coming to the the action of not like liquid. What is the value if I take 45 degree will remain so many? So really to be thought what we can do for them, that from May 15 to June 15, the daily proposal college and it was 2043. So just imagine, and when you have 119 meters, really no food have to pay. Vulnerable sex. So and so the impact of forecast is the second generation. If I talk something like severe weather, heat wave, or something like that. But what it will cause exactly? What scale? What color code? That kind of thing. So you can see, we have seen also that you may have a very good weather forecast in one year, but if you cannot sensitize, when बारिश आ रहा है एकदम आप, you have to put that emotion that earlier. So that only IGF can bring in. Okay, जैसे all IGF को भी होगा, all time we stop 3 ago, say from morning 7 to 11. The person will prepare mindset for going to prayer, food, everything, water. वहाँ जाके अलग अलग नहीं करेगा. That is the first level of control. So you can see like you never face like Uttarakhand. You have the event, but before that, you have prediction system. 5 days, 7 days, we get some signal. We click on to CM office, please conduct a meeting. They conduct a meeting 3-4 days before, they stop the visa. Things are okay. So I have a comparison, you can see that in this, I'm the rainfall amount was very high. Earlier, if you compare with that, the higher Himalaya, that what happened in Kerala, the rain was comparable. But you see, topography are different. I am not comparing, but what I want to tell, the scenario is not like whatever rain. In Himachal, you have not got 7,000 anywhere. Last year, we had a very, very repeated event like Kerala. But because of the traction, 4 pillars, what I defined, we know these areas, we know the rainfall is occurring. We have a good monitoring. And according that, we convey. So you can see the loss in 2020 and loss in 2021. Really absurd that any investment in RE1 highly return, it gives high return. So how can science deliver the last? So what you need actually, you should know, they must know what is the scale of the data. They must act upon. Okay? If you are sending something scale of the data, each individual, each community, or disaster manager of the administration act of need. We know Delhi flood in 1113 July. The Supreme Court the rainwater came. What is it been say flood water another Jamuna water would have 1 feet and a half feet. From half of the population Delhi would have been in the vulnerability before. Because it was just crossing the rain coming to downside. So that is the kind of things that we must act actually. So a fundamental change, what is the case actually? Fundamental change from what the weather will be to what the weather. That's the kind of you are giving it and actually you are telling the impact, go to safe place or you prepare actually your back, be ready for the next whether to second year or not second year. That is the scale, the idea to preach it. So it is simply actually don't keep in your pocket anything to give to the pocket. So if what the weather will be, say I have a rain gauge, so my rain gauge recording condition. आप उनको दे दो ना कभी, पास करो, and give the extremes also. इस आज का जो rain है, temperature है, today temperature, how far it is compared to earlier rain. Because as you know that extreme is an indication of the frequency. So the observation is the first part of the. जैसे बोलते हैं ना ऐसा हो गया, हिल गया. So that gives you the answer traffic slow होने वाला. Yeah, this highway will get slowed down. Or this road on the hill may get left side, something like that. So observation is a part of the that system. And coming to the you can see that you have any risk analysis. This mother and causes don't go very hazard model like I should have a landslide model, I should have a flood hazard model no. You can have some analysis this mother and threshold of this mother what we know from our when we live in village some station like Mahanadi, that if it will rain in Raurkela, Sambalpur, Mahanadi, product. So in that way it comes. And this is you can see the extreme how it translates to different hazard depending on your historical data. What is the impact estimation? You estimate just and response. Response should be there, like market can be closed, something like that, and what. So I will not go, that exposure means who is there. You are monitoring over an area, you see. Here, army camp, airport, hospital, just that. Vulnerability means I told that you have historical impact. So what threshold that area gets flooded or what threshold the site, not operate, something like that. And the risk as that takes care of everything. So these are the three we know that these are the driver of the your all services. And the risk as it adds up as the society grows, has more exposure, metro, everything you want. So risk is more mobility. The family can see highly vulnerable and under high risk every time the house breaks. But they are trying to, other way, come out of the risk by constructing it. So that way you can have a long term plan. Like that. So the methodology, this is multi, kind of subject, multidisciplinary subject. As I told whether other impact. Also, the core pillar like alimony system. So, in view of that, the very good books actually that book. You want to get two documents 2015 and 20. So it differentiates with different other country, national meteorological hydrological service. We have any publication like this. So I'm not when we approach this project, we did not go, mathematical. We just took whatever data. In very rich data, all data. So we started from 2019. So can see this is the scale. So if you are living in a community, look at postal. अगर मैं गंगा का किनारा हूँ, come in the school, मेरा घर कितना distance? You prepare, like that. This is main work. What do we do actually? We try to give reliability. What is the likelihood of temperature demand 45 for next 5 seconds? And then value as I told you 45. So we take the weather parameter as a hazard. So hazard intensity मुझे मालूम नहीं. I can take threshold of my forecast for temperature, rainfall, or rainfall. So I can directly tell the airport will close. I can directly tell if today don't go for work, 45 plus will fall and die. So that way we actually are doing. So we put the rain bar temperature is 45, and in all we have a multiple model WRM, global model also WMGSM. Estimate of it. So out of four are predicting the temperature. 100. So probability high, temperature is very high. That is possible. High estimate. Rain. So we put Delhi rain on say, Hyderabad rain on Chandigarh rain like that. Coming to so very clarity. If you put all these end to end, you can say more life, the sector will be less vulnerable for bacteria. These are the, as you know, as I told hazard, India में hazard किसमें हो? Yes, I don't understand. Heavy rain है, fog है. This is the clear cut. Dust comes are there, but these are the best. So high hazard impact vulnerability and exposure. So we are working around these actually. Global consultations come out. If you are doing AI, anything specific, you look at end to end. What I am doing, if I am doing weather model, just one person. Yes. Other impact vulnerability and exposure for whom you are working in. Coming to this, now we can see rain. We have a unit from 11 to 21 in 2021. Just I try to excite you about the severity of the heat. Whereas if the rain was every day, I have plotted also. You can see how much rain. This is something 80 centimeters, 200 millimeter and above. The rain is एक दिन कम हुआ and 3 दिन it was above 800. Such a long spell in that year it is the extreme for in the north. 2021 June, fairly bad monsoon. It is well documented. So what is I am just getting your attention, the kind of different hazards and impact a rain can cause it. Now, let us go to the Maharashtra. Similar almost, very prolonged. In July 19 to 20. Satara, Kolhapur, 455 districts, and you see the rain, like there the rain was 3 days, more than 800 or 600 millimeters. Here also the rain, see how much the rain. 400 millimeters, 300 to 800 millimeters for 3 days. Each day in that case is more than 2. So this is kind of spare and the extremes. And so you can see the different. I was talking about inundation, so how people struggle actually, and Mumbai comes in that also. In recent 5 years, that was the highest impact in Mumbai. So what I want to tell, this is a different kind of impact, like agriculture, like poultry, like animal, and no electricity for months, and the infrastructure damage, because that is highly developed area. What happened? Imagine everybody knows last. So I mean, even though you are a forecaster, what you will convey actually, so that they can close and remain safe. That is the kind of action needed actually. When you see Mandi and other title what happens. This is the Chennai problem. So the hospital we कैसे सिटी में हो जाता है पटना में हो लखनऊ में हो चेन्नई में हो मुंबई में हो तो बहुत सफर आदमी पेशेंट है को निकालो लेके like पानी एयरपोर्ट दिल्ली एयरपोर्ट 3 times we have gone inside this remains actually very challenging. साइक्लोन आप लोगों को बैठा के लेके चला जाओ 3 दिन लाखों खाने तो हो गए ठीक है महीना है कितना डिस्ट्रिक्ट from UP to Bihar to Bengal, how many people will put in the feed them to keep in the air conditioning? Well, you want to save the people, like this is a fact. Actually, the heat wave remains most challenging area in the end-to-end services. Very honestly speaking, you can see any month you take, the other month the temperature breaks the record. That's what extremes are new normal. Extremes are new normal. What means is that last year you got some high temperature, thermal negative. The next May you get other thing. The scale of the that is the scale. I'll just give you the example of last 2 years, 2019 and 20, we were not having any, but 21 actually. 2019 we were having it. 2020, 2021, no. 2022, the heat wave developed in March. Actually, February was unusual temperature. When it developed in March, the wheat production reduced by. Okay, you are having the prediction. Like how to connect with the agriculture. So that 2022, it was more impact on the agriculture because the heat wave was in March, not in May. Area, we can see the area. Exactly the heat wave, no heat wave over here. When we came to 2023, you know what happened to UP and in 2020.
Can you tell us how this data is gathered?
This is actually heat wave days.
The stations everywhere which are automatically measuring temperatures.
We have actually, as you know, sir, we have around 350 stations that we count as the cluster. So where everything okay. Everything okay means they are really validated and the calibration has been there. We call it global climate station. So these are the global climate station data which tells the temperature anomaly was 4.5 or more and temperature actual was 40 degrees. So that is the heat wave day. All day. So temperature maximum in 24 hours. I mean day maximum, because that depends fill factor. So if your temperature is very high, say 44 or 45, the person has to be in house actually. And if he is working, he should work in a ideal condition, not in the infrastructure sector. Yeah.
So how many times are you taking a temperature in the day?
3 hours, 3 hours, 3 hours.
And the maximum is over those 3 hours.
Over 24 hours.
Over those 6 readings in those 24 hours, or all the 24 hours.
No, we have a thermometer actually, sir. We have, it goes on rising. It's called maximum temperature thermometer. So there is a actually theory also, and in that thermometer design also. So it will only record the highest and remain there. Minimum is like that. So we have 3 thermometer in this observatory, in that screen actually, ideal screen, that white box, we call Stevenson.
And that's 350 stations.
Yeah, around 350 to 400 stations, which are taken yearly 24 into 7. And we have a AWS also, automatic weather station, which takes also maximum minimum. Similar way, but each 15 minutes.
AWS
We have around 1200. Yeah.
So all that data is available?
It is available, but period may be shorter actually, because the AWS, some of the AWS are very recent, but these temperatures are very long. Like here, Chandigarh, Vishal, Rohtak, we have a very long period, more than 50.
Your IFT applications are too good. They are for some stations are more than 100 years old.
But just 3.2.
Yeah.
So there are within the 12 months, there are a lot of private stations,
Like
lots of private stations.
yes, they are
My concern the private observations are there are some guidelines to put the observation, WMO guidelines. Otherwise, you cannot standardize. Okay. So private parties want to wherever they get the space they put. Maybe they have a 10-story building or inside the bush, inside a forest. You cannot put like that. Temperature means it has to measure the environment temperature. There has to be a code, it should not be in a nearby big building. You cannot keep it in the 10th floor, the top of the 10th floor. There are some guidelines. I basically follow. Other people don't follow. That's the only problem. So standardized is a problem. So standardization is a problem.
because
They have their own business. I think has its own business. So business has to beat each other.
yeah,
where institutions are managed.
But actually, like sir told, na, sir, actually like extremes. So if I put not in ideal condition, then like any floor anywhere, temperature may start 40, 51. And many times this year, sir, because like we know that Mangesh put one station, how much do you want? That cross 51, then we have to go with our, hand over the equipment, camp there and look at that sensor, then this sensor and try to get 49.5. So 49.5. So like that Barber and Churu, they cross 50, 50.5. Very difficult to, face the world community. If any station comes 52, we will be very negatively targeted in COP and other, you are the biggest greenhouse and your temperature is. No, it is just the government cannot give you increase actually. What is happening?
It's a beautiful concept because every year we cannot the identity where people are really working. We need to give salary. It's an infrastructure, it's a huge investment. So everybody is the best solution. The problem with India enterprise means people assume that if you once you install it, it automatically go up. Years together. It's not being it's not electronic instrument. But you go and periodically maintain it, change the battery. They don't. For example, I will not tell the organization, they put thousands of retailers. If they really want to do an R&D, they're searching for where is the retail. But by the time the big things have come, pushers have come, they have to go inside the booth and try to find out what they're doing. So they cannot do that. And I am planning now 10,000.
Yes, sir. 10,000 in Panchayat Mausam Seva, planning I think 4 lakhs, 4 to 5. But like sir, you told, na, the temperature is here, we have monitor. Like in Delhi, once this was out, otherwise other 16 they continuously get. Maybe it is good to see have a. But I was telling sir, this 2022, we have give you a day in just give a day in the city from 1st March to 82. Total days. Simply the frequency of a day. So what do you see? Please see this slide. You see high plus 40 reducing having 3 to 5 and nothing is there. Come to 2023. As I was telling, no heat wave in May, April, March in 2023, certainly in June actually. And where the pockets where maximum people like banana, those well, Hagalpur, so much impact because that is the period you get, the humidity of. I was talking, the vulnerability and risk. The heat wave in March, April, 45 plus cannot be compared to heat wave in June actually, East India. Very high humidity really kills the people. But if you come from this year actually, 2020, very huge, pan India. So that shows how much, things are happening. And this is the month April. So more in the second half, May to end. It's just like 2023, but 2023 just a brief of it. But 2024 is all humid. No way. So it was very drastic and very high density. Something in the record. This is the monthly actually. What do you are very bad for the crop area, like North India, that is period when the we get occur. And this is the April. April you have, but as we move to the June, it's very normalized. But this is 2023 I was talking. Only in good nothing. And when you come to 2024, you can see whole India in May, North and Central India is good. So you can see it is more in the western, it is more in the eastern, it is more around the east. That is the pattern. And what I like to show, so this month, this is the kind of heat wave you got, nothing in 2 years like 2021, and you are getting suddenly. So you prepare it. Not see the ideal. So that means your development process end to end should be, well prepared, well built, all the things actually. Like, yeah. So like I was talking about, how we actually started working for this end to end heat wave early warning system. I will just go to the similar prediction, how we handle 2020. So, sir, I was talking about daily temperature in 2024 or 2023. It's just like this, hold up, 42 in 28 March, slowly increasing, and ultimately, you end up 48. So 2024 was like that. gradually increasing and making northern parts of Delhi, like towards the area which is more towards Haryana, things like that, they get inverted double than the here in the summer. That's natural because the bees well, river side, they get less. I am talking again with the micro. A district can have a block where you have people, having more PUF impacted. So that is up to know. So you can see how the 7 p.m. you see the temperature. So even 42 temperature where there is 7 p.m. over north state. This is the high area. After this, they'll go to the. You can see how the temperatures 45 clock. Say 11th June, reducing. So they will get and you can see a scale actually. So this is very interesting scale. Like we are a GPL scale. Put it on to the May. Yeah, we know the arrangement. Okay. Second spell you can see. So like that spells comes and in. So I was telling the duration of the heat wave that are to be reached actually. So like this spell we more people die in this spell because it is in the June. But this spell it is more intense and more area wise the main but this is this spell during May. How it is figure, how it is spreads and during intense, but the June spell was it. Coming to the prediction system, I will first go to the yeah. These are the different layers of data we are working in. We have this is the vulnerability of this. You can see impact or is on the Eastern India and Rajasthan. So this is the cost where we work actually. Month-wise also vulnerability risk is there. A heat wave in June, we know it is a red color for Odisha. Heat wave in April or May in Rajasthan, we don't give any prioritize. In June only, so this is our forecast system. We are similar. We give a signal prediction by part of the first month. We follow up in the extended range, giving weekly update. We follow up in the daily update. I tell them in advance, identify the exact area. Then in the short range, we do also. And as you know that our partners who are with MSA, NDMA, SDMA, all the state secretaries, we have a email group, WhatsApp group, all these are there, and then different service sector. And when we come to the monitoring and forecasting, have around as I told, so many states we get the data they do not go to the but we have different transport, medication and 45 of where it went. So something this way we give it way and we have different heat other parameters also high temperature, maximum temperature, persistency of the heat wave as day 3 and day 4 and day 5 because longer is the heat wave, the impact will be more. So those things we are taking up. Not go. Please see the slides. So this is the seasonal forecast. You can see, I think this fantastic forecast of this. The left side is the climatology, middle is the forecast. All area with the intense rain over Gujarat, Central India, Western India. Realize this. The right side is the total day, middle is the predicted day in on first March. So this seasonal come to the this one, that monthly. So if we see monthly, we see March forecast left top actually. So what we told, there will be some heat wave over how can the forecast we are given, then you can see the realized actually. Central India we got actually peninsular Argentina. If we come to the April, we told Eastern India, South Peninsula, and part of Maharashtra. So you can see Eastern India, South Peninsula, only got. May month, we gave large part of Central India and Northeast India. You got, I am talking the highest frequency. These are the anomaly. Highest frequency anomaly. And when you come to the June actually, North and Central India, you can see North and Central India. These are the weekly. Say each Sunday we bring a bulletin where we keep the probability. It's a week one for that 2 to 8 men. Today is say Thursday, so we give next 7. So in that next 7 days, what is the observation? The green map is the observation. The probability you can see different, low, medium, and high. So you can see the area observation we did in the extended range matching with the people. So I think sir, actually that global model really helps. Really, I cannot imagine that if you have a global model, both from CFS you have American, integrated for Indian, all kind of weather system or PD. And second, you have also implementer model or LCA method for this one. The two models you have, so you are having monthly, you are having seasonal. They have also, these are the weather model I was talking. Also, in the climate model, we have similar things. So when you have a global model, confidently. So these probabilities are how we have drawn. These are maybe hand drawn. Hand में हम लोग बनाते, but we look what is the footprint of the pen. That means we have done. So that actually thank you.
So thank you, Rajendra Kumar. So any questions to him? Was talking about IMD's efforts in prediction.
You have your model and you have a lot of data. So have you correlated the model with all the data that you have? Because your weather stations and all of them are giving you. Your model is predicting something. And you have all your history of it.
Yeah, model skills, sir. We're talking model skills.
So model verification and using the data, is the model getting improved? That means, are you fine tuning the global model based on your data?
Yeah, we are doing actually that model statistics, model diagnostics, and also aligning with, suppose some events is growing. So it may not give actual temperature 42. But if you long period model predictions are available, day one, day two. So if you relate with the actual observation, you may get some, error. That error bias you can correct in the year time. That's it. Yeah.
Can we not pre-compute the hazard situation? We have so much of data.
Sure.
So if we pre-compute everything and keep that in various ways, then AI is very predictable.
That is the message that today I want to give our university, whether you call IIT or any national institution, they have to work on this hazard and the risk. You have the data, but working and getting the vulnerability and the risk is difficult, like, mathematical methods, because the parameters like exposure conditions are livelihood, many things. How much you, yeah.
So for that, if we computed and very rapidly be able to do it.
Some results are available.
No, but we scale it.
And we need this data support.
What?
You cannot simply expect IITs and universities to do research for IIT. You have to fund the fund.
Mainly data.
Sir, I've done some detailed vulnerability, I think nature may have it. But that's still going to district level going
And
to.
what about others? Cold wave?
Yeah.
We know where the folder can occur, what is the frequency, what is the problem.
For example, for the temperature on the website, you have 1 degree by 1 degree.
Yes, sir. Yes, sir.
Really, but much more refined data. Right?
Yeah, 2.25 something.
That's for Delhi, an average temperature of 38 degrees. On the days I know it's 40.
This is the data. 1 second, I will take. We have put some form actually. I must show that. So if it is, this is we have prepared, sir. Very normalized way. Checking different weather parameters. This is our website available freely. Month-wise we have done for various, weather events like fog, thunderstorm, heavy rain, and also hazard.
Next slide. Available at IMD, Pune office. Okay, thank you. Thank you. Okay, so we'll move on to the next one.
Now, my turn.
It's unqualified.
Nice working with you.
I don't want to.
Isn't Kerala. So the next presentations by Jayanar. Yeah. He's basically an oceanographer with the MSc from the University, MTech from University, and did PhD from University of Bremen, Germany, and followed by postdoctoral program of the CNRS client. So then he is the associate professor in the current course, and that is the specialist in modeling. So it's 40 minutes.
Just good afternoon now, it's 12 o'clock. Try to finish in 40 minutes. Thank you for this invitation. Give me the opportunity to talk about. Actually, this talk is based on what we are doing. And basically, finance management, it's not a rare or a but we use ML techniques just like any other tech. Like I used to draw figures with idea, for example, or math level. We use Python for programming, examples like that. So in these ML techniques also just like a tool for our research. So here you actually wanted to talk about application of climate science, but then I thought there will be talks regarding that. Then I thought there will be students. So how we can use the same techniques in scientific forms like atmospheric physics and chemistry. It's also very important. The first part, because all physics are going to know, which we have modeled before. And the chemistry is a new part. Actually, this is just starting application of ML techniques. We have just started working on. So I just wanted to give you what we are doing and how you can apply this and what are the issues that we face and what you do or what you should not. Okay. So you know that there are different techniques in machine learning, like supervised, unsupervised, semi-supervised reinforcement of learning. But technically, it's just like a subset of artificial intelligence that enables computers to learn from and make predictions based on the data. So the key thing is data. Okay? Whatever method you use, and that's also the first word. You have machine learning, you have supervised learning. In supervised learning, you have forecasting, and you can also you can make classification and reinforced. You have even game A's and unsupervised. You have structured discovery and many other things. So in application in climate science, it's very important because there's huge volume of data you handle. So that's it. One of the biggest advantage of using ML techniques are a variety of data sets you can use, and you have high dimensional data sets. You can recognize the patterns, and you can also extract features, and you can automate your programs, increase efficiency, and you can also integrate diverse data. And indeed, you can use prediction models, like climate prediction or weather prediction, and you can also assimilate data. These days, it's very important assimilating data because for model, any dynamic model, you have to give a structured data set inside the model. So we were talking about the measurements, right? He was talking about the 350 stations are there, but these station data does not go there. You have to make a grid. You have to make a structure and you have to make a grid, and then only you can fit that into model. So you can use that, and then again you can use image classification feature and risk assessment. And you can also assess pollution in the city. For example, Delhi, it's a big problem. Pollution tracking and prediction, and then you can also predict floods. Many people are working on flood prediction models, particularly urban floods. And then the question is data source. What are the source of the data? And before going to that, the important thing is we need accurate and comprehensive data. So I was asking this question, whether you validate this data. How are these data? We'll come to that point later. But data are key. And then about the sources, you have different kind of sources, measurements. You have laboratory data. You have remote sensing data. For example, many satellites are there. You have historical data. You have model data. For example, big climate models, you can, if measurements are not available, you can take model data. And then you can also have surveys, either geological or any other. Then we have also problems or challenges here, but this slide I will come to this slide later. But we can also do something about this challenge, like you can advance in terms of use your machine learning technique, whatever that may be, but you add some another analytical together. And then another way to handle this is manage your data. Now let's look at the application side. These are the case studies. These are the studies that we have done. It's just like case studies. Let's start with this question: how the statistical relationships are analyzed. For example, this is application. Mainly, broadly, we have three applications. Okay. If I use one of these ML techniques, looking at whether to find a relationship between maybe just two parameters or two variables, or in physical terms, two processes, something in there, whether it affects here. For example, you are asking how outside temperature here. Okay. Maybe today's temperature is 26 degrees, and whether this has any connection with today's rainfall or today's rainfall. And how do we find it? Usually you have two sets of data. We find two simple correlation. Usually we do that. And the methods we have, you can have multiple correlation or MLR, or you can have principal component analysis. You can use causal analysis that we do these days. Okay. You can also do trajectory analysis. When we were talking about Delhi pollution, for example. Okay. We are also talking about some stubble burning outside the Delhi outskirts, and then whether it carries pollution or not. So also an attribution, like, okay, the trajectory is coming, for example, the trajectory is coming from this side, okay, this side, you have high pollution, so it is coming. All these air masses bringing those pollution to that city like that. So there are different ways to look at the statistical relation. So it's very important, this word. That's why I put that in red. Okay. Sometimes you can correlate any two metrics. Okay? These are just numbers for a program is there. For the program, what? Whether this is temperature or humidity. For that program is just set up two metrics, just numbers. We interpret, right? We interpret this is temperature, this is humidity. So these are statistical relationships. You should know what you are doing. Can we do this after talk? And then now, so we're talking about climate, and then we have this global warming. Whenever we talk about weather or climate, we start with right. Let's start with temperature here. Temperature is global warming is happening. That means the surface temperature is increasing in the world. But this temperature increase or the distribution is not uniform, or the temperature increase. The trend in temperature is not uniform because there are many other factors involved in it. So if global warming is happening or temperature in India is increasing, these are results for India from our studies. I'm not reading that. So we want to do something about it. If there is a problem, then we need a solution. Okay. So our problem is temperature increasing in India. We know that these are the emissions. Okay. Anthropogenic emissions, for example, CO2, CH4, and 2O, tropospheric ozone. These are four important gases. So you know the problem and you want to solve it. So how to solve it? Then you need to know the driver. What drives this increase? Or what drives the disparity from one region to the other? What is the reason for this? A cause. We need to find it. So one way to do that is, okay, you're talking about temperature. then you are finding, okay, that is changing from one region to the other. You are looking, okay, what are the drivers or what are the parameters? You are saying that, okay, temperature is affecting rainfall. You say that. Okay, then now you just start with any model. You just start with a simple regression equation. Y is equal to mx plus c can be conspiracy.
Yeah, the temperatures are the temperature, system temperature.
Anything you can take this. This t can be anything. You can regress it, even daily data. So when you start with any model, any simple model is a form of a small regression. Y is equal to significant 0. That means you have to give your data. Like X is the data you give, and Y you will get. And then you say that, okay, humidity is a factor, or today is so we feel more temperature. Then you are M1 X1 plus one term is there. Then you say that not only humidity, there was rainfall, then you wanted to add rainfall. Then there is another term comes M1 X1 plus M2 X2. And then you are saying, no, there was clouds and there may be some sort of radiation interruption or something. You wanted to add the cloud term, then that is the term of M3, that's the coefficient. And so whatever you think, your model is your model, your thought. You think that, okay, temperature is only affected by humidity, then your model is just one. And but you can also add many of these, but we don't add everything. We think that the dominant factors, we think that these are mostly contributing, the others are insignificant. So the significant terms you add. So that's one aspect. And then you can also see one term here, right? And so in climate science, these kind of functions work with large scale circulation, for example. And so it's El Nino Southern Oscillation. This is the terms. If there is a change in surface temperature in the Pacific, usually in November, December, those months, January, and that could affect different climate patterns in different regions of that. Even in India also, it will affect. You might have read the newspapers that, okay, this year is El Nino, so you have warmer temperatures like that. That's one manifestation of that. So you could also add such kind of thing. And then you regress it. And then you regress it. And then you will find the contribution like this. These are the contributions written in different temperature homogeneous regions in India. Okay. So these numbers, and you can say that this is eastern coast and this different, for example, and so here very more contribution here. But it's TP, that is the pressure, its contribution is different. So that means if you regress it and you do that for different regions, you will get contribution of different function, and then you will find that, okay, if this region humidity is affecting more and the other region, like so. This is one way to attribute. This is one way to find the drive. But here is a problem. Because these are linear. Nothing happens in linear outside in the real world. So there are many non-linear complex processes, and then this correlation-based analysis or even the regression is not. It's insufficient. And it is particularly when there is another variable of a covariate is influencing the both of these. So here comes the causal analysis, one of these ML techniques that we use to find the relationship among the drivers, not between one and two, but among the drivers. Maybe X is affecting Y, but X is also affecting Z and Z is affecting Y like that. So this is not possible linear analysis, linear regression. So in this particular work, we were using a PCA-MCI causal analysis. And you know that it's initially it estimates the partial correlation between two time series. And then it finds the statistical significance of each of these correlation. And then there will be a number of tests will be performed, and you will look at the statistical significance. For example, you can define that. Two things you have control in it. One is the time delay. That means you are saying that this process will be affecting temperature in 1 month lag or 2 months lag. So you have control over that. Second thing is the significance threshold. For example, when you draw the causal relationships or the causal graph, you are taking only, for example, 95 CA. Confidence interval you are setting 95. You can also reduce it 85 or 90 up to it's up to you. So these two processes you have control, otherwise the other things will be taken care of PCM stuff. And then you will get a causal graph like this. You can see that it's entirely different from MLR, those contributions you have seen. But this is temperature and these are different drivers and these numbers are the lag. Example, if you do not find a lag, that means the relationship is instantaneous. Something happens there, at the same time it affects the problem. This is, for example, humidity, and this is precipitation or rainfall. It affects temperature. This humidity affects temperature, but there is no connection. Heat flux and temperature here. Here is the point. You should know what you are doing. And if there is a graph, something like this, we need to explain this. Okay, it gives you a graph whether it makes sense or not. So this is for all 7 temperature homogeneous regions for India, just like I did for the regression. Can we make it now? You may please note down. Thank you. And you can see that in different regions you have different connections and different relationships. For example, in some regions you have direct connection and so on temperature. In some regions you do not have. And some regions you have reflex connection, in some regions you do not have that direct connection. So what I'm saying is, when you have these graphs, you have to make sure that these graphs have some sense, in physical sense, okay? And whenever you have this humidity and there is no connection with temperature, maybe that's a false relationship, like that. So we publish this in this journal. And when you do this for different regions, it is also a test for your body. And just like data, we also need to test out more. Whether it's a causality or anything, you can use different code. I use PCI for that, but you can also use square causality, based like any other. But you also need to test it. So this is one of the best test beds for your model, whether your physical model or your statistical model. This is the region called third pole. You know that there are 2 poles, north and south, North Africa. And there is another similar kind of region. Similar means not very similar, but you have also largest ice mass outside the pole here. That's why it's called third pole. It spans 12 countries in Asia. This is called the water curve of Asia because the largest 10 rivers you take in Asia, all are originating. So that means something happens with the ice melt in this region is that we are in state of. And there will be also floods in these regions. You can see that in the Ganges, all 3 rivers are shown here. It's also interesting and in the climate point of view, because you have westerlies from the side, so this region is dominated by westerlies. You have East Asian monsoon region here, this region, and you have Indian summer monsoon on this side. And this is the desert region. So this is a very good region for testing your model, your statistical model. So we were looking at what is happening there. In all these 4 regions, and we have 4 points, R1, R2, R3, and R4. And you perform the causal analysis with snow melt, melting of snow, how snow melt is impacted by different parameters, or different factors, parameters. For example, North Atlantic oscillation, Arctic oscillation, these are some climate anomalies. And then we will find that the features, all these different regions have different features, all those features have captured causal analysis as well. And there some are instantaneous and some there are time lags. time lags are also very important because when you have something, if you are looking at humidity and the temperature connection, and you get a time lag of 4 months, that's not correct. That will not be working. So you have to be very sure about the result as well. I am not reading out the result. What I want to tell you is you can test your ML model with this kind of different regional analysis, but you also should know, in order to interpret this, you need to know the physics, what is happening there in that region. So this was also published in another paper. And then water vapor, the largest greenhouse gas, you know that. One of the biggest reasons for global warming. So here, 3 cases are there: Arctic, Antarctica, and tropics. And if you want to look at what is happening in your model, there is another. This is another. For example, here Antarctica, and this is here you have Antarctic ice as a parameter here, and then you have another one, North Atlantic Ocean, that is the northern hemisphere, and this is southern hemisphere, right? You see that there is no connection between North and Atlantic Ocean or whatever here. So that means it should not give that you also find it. On the other hand, you have North Atlantic Ocean here, and that affects that mid-latitude of that region. So it is capturing that feature. And if you look at the tropical region, you know that you have a lot of water vapor in the tropics, almost everything affects water vapor. Your model captures that very well. So this was also published in another journal. Now we are coming to chemistry. So we are talking about application of ML methods for finding drivers, finding relationships, and how you interpret. If you have a data and there is something anomalous, whether you can interpret something with that model. So this is one of the first papers published in public chemistry applying ML on surface ozone in Antarctica. We wanted to look at what is happening in Antarctica. This region is very important because first climate signals, climate change signals will be emerging in the extreme region. So if something happening there, you can readily visible. So that is one of the reasons we wanted to go to Arctic or Antarctic for this extreme regions weather. If we find there is something that is happening there in terms of climate or not. So this is surface ozone data. So now we are coming to chemistry, how we can use chemical techniques in chemistry for interpretation of making the data. So these are the central pollution control board measurements in India, different regions. We don't have any measurements in Kashmir. We have only few measurements in Northeast. We have hardly any measurements in the desert region of Northwest. And these are the seasonal distribution. Now, you can use the same kind of regression to interpret things. For example, what is the contribution of meteorology, temperature, precipitation, humidity for changing ozone in a particular region? You can use that. And but it's chemistry, right? The chemical compound. There are also chemical reactions. For example, surface ozone is produced by, it's not directly produced, it's produced with NO2 presence of VOC. You also need sunlight. For example, so you also need to have chemistry in it. So one way to interpret this is you can apply this equation, and then you have your measurements. You subtract it, then you will get the residue, and then you can say that the residue is from. For example, these are the chemical types. Okay, biologic formaldehyde emission or NO2 emissions, and you can use different meteorological types. Right from boundary layer, height, total cloud cover, and then you use this regression equation. Then you can make the data just like this. You have the regressed one, velocity is red, and you have surface ozone in blue, and this the difference is what you interpret as chemistry. And this is one way to do that. But our problem is, as you said earlier, our measurements are false. You don't have, and these are not continuous as well. So if you wanted to analyze what is happening in terms of pollution, because surface ozone is very important, it's a greenhouse gas, warmth atmosphere, and we have one even up to 0.4 degree centigrade warmth atmosphere. And it affects agriculture. Directly affects agriculture because if you have more pollution, your production is lower, and it also affects health. So its impact is threefold. That's why this analysis is very important. But we don't have data. This CPCP data are not enough to make an impact study. For example, recently we studied that ozone distribution in India, whether the NCAP, our policy, there is a national pollution policy is there called NCAP, whether it is working or not. It's implemented in 2018, whether we find any reduction in pollution. So in order to do that, you need data. You need continuous data. You need data differently. Here, one way to do that is you use an MLT. Okay. So we use this machine learning based approach to make the data, to make a gridded data to all over India. You can also do that with stats. This is the traditional method that starts like this based residual collection method. For example, you have ground-based measurements, and if you have satellite measurements, then you take measurements here, interpolate that, and then you can make the kriging method, simply interpolation. Okay, and then you can make the data. This is also weighted by you. You can have a Gaussian, and then you weighted interpolation. You do that, and then you will have a calibrated data. Means you have measurements, you have also satellite. You find the difference. You have the data. Then you do this interpolation, kriging. Corrected data. That is one way. But on the other way, using this ML technique, you have different decision. I think we run 1,000 decision trees here. You have trees, nodes, and different combinations, and then you will have that data. Each decision tree is constructed using a random subset of different features, and then you will have the predicted data. Now you see that how different and how good is this data. So this is the Indian map. You have different tribal regions here, and this is the residual correction method, the data that you made, and this is with the random forest method. So you look at the differences, particularly this region. We told you earlier that we do not have any station data in the office. So it overestimated because machine learning, they know that they do not have data, so they have a high side data. But residual correction method, they interpolated, it's a flat interpolation. There is no consideration. This is the advantage of trees. So this data we compare with other measurements, this is much better than this one, but you have to be very careful about it. So you should also know what you are doing and what is there and what is not there. So you have to take care of the data very well. So this is the second advantage. You can make data, and these data are important for model. For more a model, you need to give the data. So this is sir asked whether you validate it. This is one example for that. We validate this residual correction method. You have a node of pad. You can clearly see the head, but when you use the random forest machine learning method, you can see that this it's not that spread, but comparison is much better. You can see the R values which close to the most close to 1. So this is one way to apply machine learning. Part of that was published recently. And today morning there was a question whether ocean carbon, related ocean carbon cycle, whether models are capturing. No, because we don't have data. You have buoy measurements here and there, the ocean, and we have PCO measurement. When the oceanic carbon is called the partial pressure, unit is partial pressure. How much is dissolved in the water? So that is called PCO2. This PCO2 measurement. In Indonesia, only one buoy measurement is there. But our model doesn't know whether this is oceanography data or carbon dioxide data, atmosphere or ozone or whatever. We just take it. Right? So one way to make the data is if if you do not have data, whether there are auspicious data available for model globally. So we used the 16 global such 16 global models and made a data set. And then this data set we used to cluster. Okay, it's a cluster. Now you have 4 clusters. For example, in this first step, you have 4 clusters, and then you have predicted. But you know that this primatology will not work. So carbon dioxide is increasing, and in tandem with that, oceanic carbon cycle is also changing. Ocean acidification is happening. More CO2 is in the water. So you need to add the trend. What is happening? So in order to add the trend, you find the trend you add and run again, and you have the final data with interactive variable. Whether you can have monthly, you can have season, you can have. So you have the interactive data. That means every year, every month you have data. Earlier you had only the monthly data. Okay. So using that method, you can really make the data, monthly data from climate change. So that is one advantage, because you do not have, otherwise you do not have data. Without data, you cannot study as well. So this is one advantage of, another advantage of machine learning, how you can use to predict models and to find the carbon cycle. So this, one of this PhD work is finding carbon cycle, ocean atmosphere exchange, carbon exchange, like that. So this is the available PhD measurement in Indian Ocean. Only available measurement. You can see the huge gaps are there. And with this data, you cannot model. Because these data are not continuous. These are cruise measurements somewhere, somewhere. For example, 93 you had a cruise, and some region you have some like these are the cruise. These are not continuous. Some year some point, some year some point, like that. These data you cannot predict anymore. So we needed data. That's why we did that. And then you can make with the random forest, you can really make the data like seasonal signatures. And this is using that random forest, we made the acidification carbon cycle. So, and we compared that with some available. You know, I forgot to tell you that when you use any machine learning method, you train the data. Either you can make it 70-30, it's up to you. Most of the time, we use 70% for training, 30%. And sometimes in chemistry, we take rigorous because it's a bit difficult. Because chemical species reactions takes place in some seconds, some in minutes, like that. So you need more training. So we take 80% and 20% for wide action. So those regions you do not have measurements, you will definitely have fireflies. You have to be very careful. You have to map something like this when you interpret. And just like this, atmospheric science, physics, chemistry, or ocean, and you can also use that in land science. We guide that whether, for example, the photosynthetic activity of vegetation in India is increasing or not, or if it is increasing, what are the reasons, what are the different drivers, like that. Apply this kind of causality to any data or any process to interpret or find or even to play. So I'm not going to the details of that. And then I'm summarizing the summary and the way forward for this. The important thing is the data. Whenever we are talking about model, without data, there is no model. So a good model can only be made with data. So more data, more information, your interpretation will be more reliable, accurate, and you also need to check the physical connection. You should know what you are doing. You should be aware of the process. And then these are data-driven models. So I am coming back to this slide here. Data quality is very important because your data is not good, then your model is missing data. You have to take care of the missing data. And there are many gap filling and algorithms as well. Data integration is important, and different types of data homogenization, for example. You have temperature data from maybe AWS or automatic weather station from satellite or any other, but how do you integrate it? These are very important. And what techniques you use? There are good techniques in ML available for integrating data, making good data. So data is very important. Then what are the opportunities of future? You can interpret a complex model and processes. You can analyze even chemistry. And then you can also have real-time data. Our biggest problem in climate science, whatever we do actually, is computing time. If you want to run a model, it takes a lot of time, a lot of money as well. So most of the time what we do, sometimes we use parameterization. You were talking about that. Some parameterizations are very important. When you talk about the climate model uncertainties, the biggest uncertainty is radiation, cloud, and then we don't even know what a cloud is and how it is forming really, and what the structure is. We assume it. We have some measurements. With respect to some measurements, we are assuming something and then we have parameters. So within a grid, if you nest it, it takes a lot of time. It's left from computational survey you needed. So real-time data processing means more time, more computing. So some of these ML techniques you can use that will reduce the loss. That will minimize the loops as well. If you check any global model, climate model, almost all models, even we are using Julia these days, right? But models are important. Why is that? Because the Fortran loop works better. Now we are changing that. Okay. If you use Python earlier, it was not possible. You can call any language in Python and then you can run. Like only you need a Python code to call MATLAB, IDL, or anything. You need only a Python code. Earlier it was not possible for us. So just like that. Now these Fortran codes will be changing. Maybe some techniques can be incorporated. So those are the opportunities, those are the future. And for policy analysis, you need good data. So these techniques are very, very helpful for impact studies. Are very important. Something is happening there, and we are also into what we can do about is very important in terms of climate change and global warming. So impact assessment studies are very important. This will be giving a good, clear indication. So, sorry about this trash word. The final thing is that in any model, trash input is trash output. That means data is very important. Data are very important. And we have the communication and the knowledge that people data providers or model gain during the mile and my our visitor here and the AD connect. I think it says thank you.
Thank you. There are enough questions. You want to talk?
Machine learning and statistical method you have done. So the Rajasthan and Gujarat region, you say there was no data. Same was the J&K, the same was the Northeast. But the way it is interpreted everywhere, the data is not there. So the bound of the boundaries or any random data in the system.
Told you the oceanic theory, correct? And we do not have data. In Indian Ocean, we only want the data. Sorry. That's true. We don't have data like this. No, we did not. We can't. We tried. How I did that? What I explained here is interpretation.
Interpretation finds once made this color predicted as more over.
No, actually, this is the machine learning itself gave this data, but this is not the fact. We have not used, but
without the it is the boundary values.
Yes. not random. These are mostly taken away from the government.
So the machine learning is on an average giving better results, but if the extreme results are worse than the residual method. What do I get as a conclusion from it? The residual method is more accurate, or this is more accurate, or
No, the machine learning is something correct.
more accurate?
Yes.
But giving more error, you said in
This is the point I wanted to make, because I made this color red because when we do not have the data in some region, then we should not use that. Should be very correct. And the first thing is, when we have something, when we make a data, we need to do this. You have to make sure that you have result as compared to available data. It's very important.
I think other than just average value, I think the standard deviation and everything else is qualitative.
Yes, sir.
And then when you came to that other one, where you use random forest to generate the data, there also did you do a study of how much data gave how much accuracy? Because you have certain amounts of data. You could have reduced it a little. Yeah.
So this is the mean absolute bias. This is bias, mean absolute error. This is R and this is R.
So what I'm saying is that there is X amount of data which was used for
Yes.
generation.
Sir.
Now, if you reduce that and still try to generate, you want to see whether that accuracy.
Yes. It matters. Training data matters. That's what I told. We use
How much is enough?
How much is
For-
optimal?
So here we use the 500 piece, and the 70% we use for training, 30% is for practicing. And if you reduce it, these errors are high. And this is optimal is something like 70. That's why we fix.
You will use generative AI for
It's complicated.
So, I think you should thank Sanjay Narayana for.
Thank you. Thank you also for taking.
If you want to comment something.
So yeah, so because we get to be a model, right now we just go to that all. It will work.
where is the line? I have to start at 1:30 AM from Kharagpur. Because now in Calcutta and Chhattisgarh, it is jam and temperatures of mind is very high. Yeah, because of the, so anywhere, anybody is angry, they will stop anything. Huh?
People always.
So I. But I was like workshop. Measurement of the. Yeah. The labs.
Yeah, yeah.
If anybody is there, other than.
Pause the recording for now.
So good afternoon, everybody. And it's my pleasure to welcome Mr. Sandeep Chakumaran from Center for Atmospheric Sciences at IIT Delhi. I have a connection with him because we have he did his PhD from IIT. So he will be talking, as you can see, on global weather prediction models. prediction of monsoon is in the field. So welcome.
Yes, sir. Yes.
You want to
I know.
Yes. We wanted to go back to the fight. We lost a good game.
Thank you for having me here today. Uh, so, I basically I was a machinery expert. I so I'm basically meteorologist. Mostly my research interest is in energy dynamics of maybe performance. By I've been working on to understand how the monsoon is evolving in a warming climate. But with some collaborations in IIT Delhi, I ventured into machine learning applications, specifically focused at monsoon prediction. So so this work is done. Whatever I'm showing here is all these works are done in collaboration with the Professor Solomon, who is faculty in engineering in also joined with the School of AI, and our PhD students. So I'm sure that Rajesh Sara yesterday talked about monsoon prediction, its details. So I'm not going into the technical details of that, but just briefly, in one slide, I talk about the logic behind different scales of prediction. Yeah, yeah. Forward. Always. So, basically, the monsoon prediction has a long history. I have read that the first official forecast was made in the year 1886 by, if I'm not mistaken, by Blanford. And ever since, I mean, every year, the monsoon seasonal forecast was being issued. So, but we know that the predictability of atmosphere is for 7 to 10 days, and in the tropical region it is even less. So, because atmosphere is chaotic, this was proved by Lawrence way back in 1960s. And why do we actually do the seasonal prediction of monsoon or subseasonal prediction of monsoon when the predictability of that itself is much shorter? So there is something we need to know here. So the within the atmosphere itself, there can be some recurrent oscillations. So these inherent oscillations can be used for prediction. I mean, that gives us a longer window of predictability. And in the case of monsoon, it is influenced by the external drivers such as speed of the temperature. So these are very slowly evolving phenomena such as El Nino southern oscillation. So when it is controlled by such low frequency dynamics, then that again gives us another window for longer predictability. That is the seasonal. So this is logic behind why we are when attempting longer range predictability than the theoretical. So, yeah, this is a nice schematic I have taken from this work shown here. So where actually nicely represented all the large scale phenomena that have an influence of monsoon, such as El Nino southern oscillation, Indian Ocean dipole, North Atlantic oscillation, and also the snow depth and the soil moisture. These are all giving us predictability in the longer term. And within the monsoon, there is monsoon intra-seasonal oscillation. So when I say this gives longer predictability, it is again not a linear relationship. When El Nino, for example, El Nino and Indian summer monsoon, it is not a linear relationship. We all know that if there is an El Nino, then mostly people say that it's going to be a drought year. The monsoon is going to be less than normal. Here you can see this is an index mode. So positive means El Nino, negative means La Nina. So you can see that most of the monsoon drought. So this is why Indian summer monsoon rainfall anomaly, or the average rainfall anomaly. So most of the monsoon droughts were in the El Nino year, so positive El Nino events. But you can see there are some normal monsoon rainfall also happened in when during El Nino years. But this happened in 1997. We got the largest or first El Nino ever in the recorded history, and that turned out to be a normal monsoon year. So everyone except IMD predicted a drought year, but IMD predicted a normal monsoon year. It turned out to be correct, but I was told that the IMD model always predicts normal monsoon at that time, the statistical model, and in 2002, I think there was a drought monsoon, and at that time it was realized that this model always predicts normal. So yes, so but this is these are so there is a high level of non-linearity here. The predictors, I mean the relationship between some monsoon with the Nino is not actually linear, so that poses a great challenge here. So
I'm not there for that coefficient of variability of rainfall. It is not happening in a there has not be the variation for the high variation nearby 1 point. Then there is so very low. So variability is very low. Normal.
so the El Nino itself is is have a longer predictability. So even using dynamical models, we get like 6 months of predictability for El Nino. So this was one of the biggest success of climate science actually in the recent history. So in 19 to successfully predict and forthcoming El Nino about 6 months in advance using a numerical prediction method. It is because of the slowly evolving dynamics of the ocean dynamics of El Nino. So this, so there is something called spring predictability barrier. So which means that before the spring season, if you start you try to predict El Nino, there is chances of getting your forecast is actually not that good. So after the spring season, you can predict it. The predictability is higher. So, but one of the reasons the machine learning models is that they were many models were able to show that the spring predictability barrier can be broken by the deep learning models. So there was a paper that was published in Nature using where they used a convolutional neural network to predict El Nino about 18 months in advance. Following that, we have done. I mean, this is the one we did with a BTech student in Nagunda, and she used a convolutional long short-term memory model to predict the Neo 3.4 index, which is the it is the piece of temperature. Yes, yes, only that. Is given us the input, and we were able to predict the El Nino 12 months in advance. The forecast that initiated in January, monthly is of this temperature basically. So you can see that three cases of El Nino are shown here. We compared that with the operational, dynamical, and statistical model. So all of these are archived by Columbia University, where you can access all the any forecast, even real-time forecast you can see. So we compared their January initialization of dynamical models and statistical models with our convolutional LLCM forecast. And we got reasonably good. So this is red curve actually shows our prediction. And this blue is the blue curve is actually the observed evolution of Nino 3.4 FSC. Green is the average of the statistical model predictions. The black is average of the dynamical model prediction, and we have also shown the standard deviation the predictions of these models. So this shows that the can actually go good when in the case of a slowly evolving system. So then we actually focused on the monsoon intra-seasonal oscillations. So within the 4 months of monsoon, if you look at the daily rainfall variability, this is taken from IMD. This is taken from IMD website. This is actually for this year. So daily rainfall, you can see there is a fluctuation. So and this red curve is actually the same climatology of daily rainfall. So if you subtract this long-term climatology from daily variation, you will see all India level data. Yes, all India daily rainfall average. So you can see that there are some negative values, which means the below normal. I mean, the rainfall is less. This is a bright spell. This was actually the last year, because this year monsoon is not yet complete. It's ongoing for you can see that there are spells of active and failed cycles. So this is basically part of the intra-seasonal oscillation. So since this is another oscillatory system, we thought that okay, this can also be learned by the deep learning model and we can predict it. So, so this is the spatial evolution of these rainfall anomalies. So from a break phase to an active phase. These groups show negative anomalies, which means the break phase, and the red show the positive anomalies of rainfall, which is when it comes over the intervention is active phase, we get a lot of rainfall. So so what we do is that we take the three-dimensional data, latitude, longitude, time data, and we apply a principal component analysis. So this was already done by previous work, previous studies. So we know that the first two principal component time series actually represent this evolution of this intraseasonal oscillation. So this can be nicely represented in a phase space diagram. So from clockwise here, you can actually track the movement of intraseasonal oscillation. From each subquadrant is identified with a location. So you can actually say that at which location is the cloud band is actually located now from this. So now there is a since we are trying to actually start a very simple prediction. We are trying to predict these indices rather than the rainfall directly, because I will show you why. I mean, it is not easy to predict rainfall. I will show you. We did that also. But these indices, we call it monsoon intraseasonal indices, MISO 1 and MISO 2. These two indices, we can actually represent the oscillation of the intraseasonal oscillation of monsoon.
Will it make sense to take all India indices together, not top India from different parts?
So, yes, so here we did not actually took area average or anything. This is the principal component. So you took a larger area, so did the PC analysis, you get principal component IC. So, so it is good. Actually, it represents all this domain.
So you took all India data, right? And
yes.
then you just kind of
Yes, yes. So if you go to smaller scale, you will have a very chaotic system. You do not have this smooth oscillation at a very small location. So for the time being, we are actually looking at
natural way of
composing. Yeah.
The rainfall is really very sensitive. So other than the scale, you may get some.
So for example, monsoon is a different component. You might not think
And I mean, I'm talking about in terms of space, the temporal oscillations. Spatially, from place to place, it can vary. For example, if you look at Western Ghats, the characteristics of that oscillations may be different from that of Central India. So, yes. So, this is, I mean, we try to model this with two different standalone machine learning models. One is a simple LSTM model, and another is a transformer. So we train, we basically we use since we also wanted to cover the ocean. So the starting this summit March last week, so Indian Ocean forward. So to completely in order to completely represent that population, starting from equatorial Indian Ocean to all the way to the continental Indian, you need to have data coverage. So right now, we have a global satellite based rainfall observation. It is called a tropical rainfall measuring mission. It lasted, I think, it lasted from 98 to it was 4 by what is called global precipitation mission (GPM). So we compared these two data sets, and it gives you like 25.6 years of satellite-based rainfall observation. So we use these rainfall observations to extract the MISO indices. We applied VCA analysis from that, got VISO1 and VISO2 indices and used 20 years of data to train the model, and then 5 years we used for validation. So 20% of training data is kept for testing. So then this is the comparison of the our two deep learning models, LSTM transformer. This is observation, black cloud observation. You can see that the transformer is mostly following the observation. And we have also compared this with the two global, the two numerical weather prediction models, ENSER and UKM. So they are also their sub-6 month to 6 month forecasting initiated on 1st June. Is taken. And these are the 10-day lead predictions are taken here to compare. So what we found is that at 10-day lead, these two ML models are good skill in predicting these indices, VISO1 and VISO2 indices. If you see the namespace diagram, this is the evolution of industries observation for the year 2022. This is the transformer, not bad. And this is the LSTM, this is ENSER. Will be model. You did not try that. Yeah. So yes, this again shows the deep learning models of skill. But this is not a fair comparison between the MWP models and the deep learning models, because here I have used the precipitation forecasted by the ENSER or UKM models and extracted the MESO from the forecasted precipitation. And here I predicted MESO1 and MESO2 directly using a model and compared these. So direct prediction of rainfall is actually challenging. I will show you that in a moment. But where we look at past 64 days of data is given, and next 10 days forecast is made. And 21 days forecast is made. But what I have shown is actually this 10-day lead forecast. Yes, that is for training. So, but for initiating, before initiating each forecast, you give 64 days of forecast. Text, right? So, yeah. One thing that we have seen is that in the transformer model, the error growth is actually very less. So with time, so my colleagues in who are working in ML, they are saying that okay, the transformer model is basically used for large language like LLM, and they are good in predicting long sentences. So this might be, I mean, this is an analog to technological prediction here. So they are already known for predicting long sentences here. So that means they have long prediction skill, long range prediction skill.
We code it the transformer or you use autoformer, reformer, those kinds of things.
So I frankly speaking, I do not know that details of that. I mean, that part was taken care of by my colleague. So this is an encoder decoder. Yeah.
So nowadays there's a lot of interest in time series modeling using transformers and
yes.
So one best product is the patch PSP model.
Okay, that we will also follow.
Patch PSP better than others.
So here is our prediction of anomalies spatial prediction of rainfall anomalies itself. So you can see this is an observation. I mean, this is a random date is taken. This is the this is 1 day ahead prediction, not 1 day ahead prediction. You can see that this this positive anomaly is, I mean, when the wise it is something it is interesting, but its strength is very, very less. The amplitude is highly underestimated. This is a problem when we try to do the rainfall forecast. So I will show you some of the models that Dr. Amal Jyoti discussed also, the global models, global machine learning models. Many of, I mean, they are also having issues in rainfall prediction. So now, I mean, here, and when we try, I mean, this is again market process only. We try to look people into this. So rainfall spatial evolution of rainfall prediction is really challenging. So then we tried seasonal forecast of monsoon rainfall using neural GC. Not just rainfall, actually, this is the seasonal forecast using neural GCM. Neural GCM is probably the most recent on the global machine learning models. It is again Graph and neural GCMs. These are both developed by Google. And this is unlike other ML models, this is a hybrid ML physics model. So which means it has a dynamical core, just like numerical weather prediction model. Is parameterized. The physics is layered. So which means some grid scale processes, typically the convection, the formation of a cloud, is actually a critical thing to represent in a numerical weather prediction model. So we use a technique called the parameterization, which is a kind of an empirical representation of the grid scale process with different processes and the grids. So here that part is laid, they trained physics module and combined that with the dynamical core. The advantage of this model is that they said this can be run for long predictions. All other machine learning models like GraphCast are meant for short range, medium range predictions, up to 10 days. These claim that this can be potentially used for climate questions also. So there is no that, but they claim that. So and for historical periods, they have done integration of like 30, 40 years and compared the temperature, and it is quite matching with the observation. So, but there is a drawback of this model. This model does not directly predict the precipitation. So, because precipitation is an outcome of the physics in the normal numerical weather prediction model, and for some reason, they found that it is not good. So, it is right now this version of the model is not predicting the rainfall. So, we did we ran it for monsoon season starting from 1st of June. And since precipitation is not given, so what we did is a simple comparison with the Somali Jet Index. So it's nothing but an average of the 850 hectopascal deep speed or here because these transport the most metropolitan area, we get rainfall. This can be used as a index of strength of the monsoon. Although not, it may not be directly correlated with the precipitation. To get a variability like this is again compared with the UKMO, also you have 5 reanalysis data, and UKMO prediction. But these are so I'm not doing a one-to-one comparison of these because when we do the seasonal prediction, you need an ensemble of forecasts. So we do not run a model one day and say that, okay, after 90 days, this is going to be raining or not. We have to do a probabilistic forecast for that. So for that, you need to run the forecast for multiple times and come up with a probability of whether it is going to be raining or not. So that is not actually done. So I'm not doing a one-to-one comparison, but these models are so the variability of monsoon, something which can be compared to the observation and the UKMO forecast. And the
model is reduced the signal.
yes, correct.
Going up,
Yes,
then July, August, then again,
yes, slightly reproduced. Not big deal actually. So it's something highly predictable. Yes. So, but they have to give rainfall and that is actually very
for you have to
for 10 days it is like 3 seconds only. Or a 2 GPU core. That is the real advantage of the MI model.
run in the quantities.
No, it's a 2 CPU not for power space. Not
These two.
parameter like that. So this is again wind field data of the wind field given by the computer. For a machine learning model, it is like monsoon, like wind is a volume. So and again the perspective of water time is not going to the unless there is precipitation, there is no much interest here. So then I will quickly wind up. We have listed the already mentioned. Global medium range forecasting ML model. So there are 3 models: GraphCast, ForecastNet, and Pangu Weather. One more from Microsoft is coming, Aurora. So the GraphCast and Pangu Weather are being run by the ECMW. They are providing the forecast of these along with their IFS model forecast. So this is, I mean, I'm sure that the ECMW may have plans to move to the base model. So it is it's big thing. So
I don't think they will.
completely move. That is what it may take even if they do, it will take a long time. So right now their skills are not actually good for exchange. That is what I am going to show here. So this is Kerala 2018 floods. So we did a 10-day forecast of GraphCast for this event. So if I use 24. So this is the time 1 means 124 hours, 48 hours, and so on. And as the lead time increases, it's the diminishing I will show a comparison with actual observation. So here, this is the GBM observation of that event. Here you can see this is the actual rainfall intensity at the right location. So you get 2 peaks here, north and south of Kerala, and you don't need to wonder much where it is coming actually. So this is 5 data which actually explains more. So they have even used the precipitation from Europe. So we never use the meteorology community. Nobody uses the precipitation from a reanalysis product because we know that it is the product of the parameterization of the model. It is actually not good. So they use these precipitation to train the model, and that bias is actually there in their forecast. So, but there is a catch. If we can retrain with our actual observation, probably this will give us the good tool to predict rainfall, especially in the mountainous regions, 24 hours or even for nowcasting. But that somebody needs to do that, retrain the model and all. But right now, they have a big problem. And now, we compared all these three models for the last 2 years of tropical cyclones over the Bay of Bengal and Arabian Sea. Because all these models were trained up to, I think, 2021 of IRA data. We get only 2 years to validate their performance. So now, 7 tropical cyclone cases happened in the period. So we did a forecasting of all. You can see compared with IMD. So I think you will be happy after seeing these results. So I will show you one. So the track forecasts are almost comparable. They all reproduce the tropical cyclone package quite nice. There is a statistical comparison of all this. So this is actually forecast error of track. Only three graph class, Pangu weather and forecast track errors are compared. More or less saying maybe these models are better with higher lead times, like 90 hours after the formation of the cycle. But track is not, you also need to forecast intensity. What is the wind speed, maximum sustained wind speed of this tropical cyclone? That is very important. So this is the problem. So if you see, this is the observed wind speed evolved like this curve. Okay, this is IMD prediction, reasonable numerical weather prediction. I think IMD WB prediction. So we have taken this data from IMD bullet and digitized and so these are the models. You see the difference. These are highly underestimated the extreme never intensify. So this is a big problem with these global models. So and people are discussing that this is actually the penalizing for the because you use mean square error as the loss function. If the maximum weight is displaced by slightly displaced to space, so you do double penalizing. One is where it is missing and one where it is actually wrongly forecasted. So that means it is actually you won't get any extreme winds. Yeah, but that is something they are working on. That is what I heard, along with Asian Wave. So we did not do anything more. Yeah. Yeah.
You can take the number of mismatches. Then another is the growth rate.
Yeah.
From this point to this point, whether the curve is moving up, down, things like that. So we have used P4 and combined them together.
I think this is the reason why meteorologists and data together to solve this. So I was told that mostly this is actually software engineers, Google and now they are actually working with Ethan way of decoding. So probably next version will actually address many of these issues. But the great advantage of these models is that if it is giving good forecast, I mean, it is extremely cheap. Once it is trained, you can issue a forecast in matter of seconds to GPU nodes. I mean, rather than when you go to exascale, your power consumption is huge. So we can have a trade-off between these two. What is coming back? Yes. So if you yes, yes. Yes, when pressure drop out, pressure drop is also not properly 950 years.
When wind speeds change, that's the incident that one function and all will be different for that because it can be.
Delivery. You have all parameters. Cloud will be missing, rainfall will be missing.
So, although I mean this is when you skeptical But I see this as a challenge for the researchers. We have a lot of opportunities to actually work on this and improve. So I summarize this. So focus of monsoon rainfall is still a challenge. And also, if you look at the medium range ML models, these are all deterministic models. So right now there is no way of actually generating answer, make a probabilistic forecast. That is something actually the ML community should actually work on. We need to have an ensemble prediction system. What we will do. Right now, what I'm thinking is that they have different flavors of models, right? So we can have actually multi-model ensemble we can find. That is yes.
That's an alternative they can do. It is not as fast as this. Is that your physics model, step by step, from this step to next step. We make a neural network of that physics model. And we simulate that step by step. So each step is taking a lot of time for solving the differential equations and all. That is solved by a neural network.
That is what they have done in neural DC.
It's straightforward thing.
Yes.
But once you do that, then now you are bottling in time.
Yes. So that is what I think also Tapio Schneider is also. Sound parameterization.
Can be replaced by.
Yes.
That's what you say. Physics can be partly replaced.
Hybrid model can be the optimal one, and that can reduce computational cost and can increase the accuracy, and at the same time we can have the ensemble forecast. If you reduce the computational cost, we can have multiple more number of ensembles also. So that will help us in reducing the uncertainty in a better way.
But unless you are able to explain it, you just have a data model, then finally you are not able to explain why things are happening.
Problem in the model. Model, we don't know if something goes bad, well, still model you can easily go and understand what really gone bad, what was the physics behind it, but one model we don't know.
It's like a blind box.
No.
Explainable and
What the feedback mechanism when it goes by?
So there are some methods. Sometimes the methods are that gross scale physics simulation of it, follows it, and then it goes back and corrects. I think the explanation why it is happening. Coming back to physics explanation, that's very
So that for 10 days is to code it 3 seconds or something. So, but to develop that neural network model,
training will be
training, it is taking a lot of time.
yes.
Huge computing power.
because this graph convolution GCM, which means for every point, they are training all the points the spatial over time. Which means it's going to take a lot of computation.
Yes, and we actually work on training. Retraining.
So very model you can just start and do it.
Yes.
But this, the fact that they've trained on the reanalysis data, then one can fine tune it on the actual data, right? So this is
Data is something, if you look at the global data availability, all continents you have like IMD information, all the agencies. Then it looks like desert over the vast oceans. You don't have that kind of dimensional, I mean, data. No, actually, what they do is that the region is actually observation. So they do assimilate the whatever observations available, like developing a data product, right? So this is such a global data product. So this is is actually this is released by the ECMWF, which is kind of best reanalysis currently available.
So my suggestion was that there is a grass model which is using PRA5 data. It's not using kind of ground data like you supposed to pair up IMD. So can you fine tune the grass model now? That's of course that's
Yeah. But patient don't take it from there, take it from here.
good. That's what I think. I think statistically can be fine tuned in that manner.
That is why I think it's possible. Yes.
That's good.
Yes.
We done by graph training.
No,
Yeah,
no,
Run it again, again, you need to.
no, fine tuning is a drop off already safe. In that sense,
No, we don't need to rerun that.
What we do is, we remove the first 2-3 layers. And you just change those weights.
Yeah, I think
Final your weights to those. It's only last year.
lot of years and put all the scientists in India. Some
No, the question is,
you are the
their model, even if you have their code, if you run their code to try to generate their model, you are unlikely to get it. Because they have done so much of data cleaning, pushing, that what they do is, they train their model, then they infer. They find Camilla, they again do tweaking and train them. So finally, if we try to train the model, I will show you another way. I've seen that in hundreds.
But can we do actually a regional web using IMD one of the things? That is something you could actually aim for.
So that was
Very maybe you're fine tuning things with the Indian analysis or Indian domain with the patient going to 100 years data.
Regional
If you do the gap plot for this.
yes, I mean that was I think I need to work with the so a regional version of graph neural network.
Stop using error for using
Yes. And even IMD presentation. Yes.
So it should be done.
no, but we can do it because we have the IND rainfall data. That's possible. It's just a matter of removing a couple of layers and putting them again.
No, but it may, yeah, but it may require a little more.
Yeah, another question, how much, what is software? Can we go and calculate?
With the gap plot, you can do it anyway.
That means I can take I can take a agent station of Kerala, which has very rainfall data. That's possible. So this rate.
Downstream, the overall takes a very, so when we downstream.
So one of the problems of solving a problem. Models are actually not getting that card. But this model, I mean, for a short range prediction, so it is not bound by that kind of constraint. If you have observation over that problem, it should be able to learn and fix. Yeah. Thank you.
Thank you.
Clear, all points clear.
So we'll meet at 4:05 for the next session, last session.
What can be done?
Yes, sir.
Yeah.
Unleash the student power.
No, this one.
And this, so finally, they are running a little bit,
Okay, so we'll start now.
Yeah, just 1 second.
So yeah, number of things. I don't really do empirical work, so this is the first of its kind to me. So it's interesting from that point of view. Started venturing into this world of machine learning and monsoon modeling last year. we got hold of some data and we kind of done a way through. I also don't have much time these days for a variety of reasons. So even just making this presentation, I could not find time for it. And neither could my two authors were all kind of with their PhD abroad now. So I asked to Meg to use what was ultimately Chat GPT 4.0. So you put the paper in it, and it kind of organizes the slides for you. So I got everything from there. It was downloaded. I think Anirban downloaded it on the GPT file, and then I just put some coloring. That's what we have here. Okay, so in your world, historical database monsoon rainfall prediction in India. My co-authors are Jatin Batra, he's a colleague at KFR. Asta did a lot of the work. She's in Columbia University with her PhD. Who initially did a lot of work, he's at Georgia Tech. And Professor Rajivan guided us with this. Right, so this is carry on. Okay, so motivations, rainfall, everybody knows monsoons are important. NWPs, as we heard even in the last talk, are not good predictors of rainfall in India. But we just say, okay, how bad are they? So we just think about that. And actually, initially we thought they were pretty bad because you would get NCEP, NWPs, a particular kind of NWPs. Later, when we done all the analysis, did everything up, we found out that ECMW, this European Center of Medium Range Forecast, has their own kind of version of numerical weather predictor. That's much better, so we'll talk about that. We're still doing better, but we have a perspective. And machine learning efforts have begun to show success in exploring past patterns and variants. That's the motivation for this work. That's why we think the NWPs don't work, machine learning methods should work. All right, so what do we do? So we will consider rainfall data which IMD makes available to us from 1901 to 2023 in grid size of 0.25 times 0.25. That's about almost 28 kilometers by 28 kilometers. We also did the analysis 1 degree by 1 degree, very simple. I won't talk. During the monsoon for 4 monsoon months and train and transform over time, so that's the auto format that we train. Make forecast for next day and for 3 days. We compare these two forecasts made by popular numerical weather predictors to high resolution integrated forecasting systems, HRDS. I'm saying it because there are a lot of kind of abbreviations going on. It must be very frustrating for people. I don't feel like it. So HRDS I'm going to use, but that's a numerical weather predictor. Good one. The European Center of Media Weather Forecast. Another abbreviation. And then it's Can we start recording?
No, I think share was stuck.
Oh, I see. Oh, but were we recording or no?
Yeah.
Even earlier. I don't have to not introduce myself again. All right, good. Yeah. So we'll compare to these guys. So National Center for Environmental Prediction and CEP, and that's what's being used by, I guess, people in PM. We compare to these, and we also use additional covariates, cloud cover, humidity, temperature, soil moisture, body, and mostly, along with any predictions input. That's the big story. I think the other big story point which I'm not mentioning here is that there's a kind of a folklore that there's memory in the data. We see some of that. So essentially all they're going to do is they're going to take so 0.25 by 0.25 grid means that there are about 4,500 grids. So IMD data gives us 4,500 rainfall data points on day D, on a particular day. Then we go back maybe 10 days. Then we have 4,500 times 10 amount of data. That becomes our input to the transformer model. And the output is 4,500 grid forecast for the day. That's all there is to it. It's not that much lot. But then you say, okay, shall we go back 10 days? Shall we go back 5 days? Shall we go back 30 days? So it turns out it matters. That once you go beyond 10 days to 15 days, then memory actually improves forecast somewhat. This is kind of folklore that there is memory. There are this, I'm forgetting the terminology, but there are trends in monsoon. There's, these active phases and passive phases. There is memory. Somehow our model is trying to that. So that's the big picture. I was just telling them, I'll tell from a person, this is my first empirical talk. I've never given empirical talk. I don't do this kind of work. But more than that, this is also interesting because I didn't take this presentation. I just put the, I didn't have the time to do it. So I took the paper and put it inside the chat GPT. And kind of did all of this work for the most part. That's also a favorite. All right, so there we go. Slide was moving. So Bhavesh not here. I see. Okay. Continue again. But you know the technique, right? So, turn that form. Okay, so yeah, there's not that much to report as such.
Present it.
Yeah. Okay. Okay, the salient contributions are forecast based on past rainfall data using auto formats basically, better than those by NWP models, numerical weather predictors. And that's because numerical weather predictors basically they rely on initial conditions that we've been getting so far. So initial conditions are all the information that's being captured by sensors. My guess is that from India, the amount of initial information that's going out is probably less than maybe in Europe or US. So once you have the initial conditions, then if you just deterministic finite the difference node by node solving of PD, apparently that by and large that goes a long way. We have about 20%, so HRES have about 22% higher error in the year one. And CEP has about 43% higher error for a single dip. And these errors increase in the top of periods. Persistence has 40% higher error. Persistence is what's the rainfall next day, same as rainfall the previous. So if you just do that, you're not doing terribly compared to what you do. So it also tells you that there's room to improve. That's something we should talk about. What extra information can we incorporate somehow to do a much better job than we do? We are just looking at previous rainfall data and a few more pieces of information. Maybe if we had data, we had satellite information data, we can bring these numbers down. And we will go. Our methods to a better job of capturing large rainfall events. Where we define this as follows, where data can stay there. Actual rainfall more than 30 mm in a grid, and we predict more than 10 mm. So then we are saying that our directionally we are doing the right thing. So we are saying it's going to be rainfall and you see substantial rainfall. So at least we warn you a little bit.
No, we also do. I never predict, the actual doctors getting one day you 190. We never predict. We can only predict 400.
So that's it. It's in that spirit, but probably not good numbers.
Thank you.
More than 200. So then we don't tell. It will be 400 millimeter, 600 millimeter.
No, but 200 millimeter is a serious rain.
But actually, it's much more. You can see. Like each year you will get, if I am correct, 2023, we have 9 cases when the rain exceeds 400 millimeters. 44 hour observed. 9 cases.
Well, here we just wanted statistics, so we are using much smaller. And then the other way around, controlling false positive. We predict rainfall above 30 mm, and actual rainfall is less than 10 mm. You tell people, oh, there's going to be massive rainfall, you should not go to work, those things down, nothing down.
But that is our case. Cannot have 100% prediction correct.
That's right.
Then we would not have to think.
So we want to compare and say, okay, we are saying the same better.
We
We can predict such a way that our wrong prediction does not make somebody who is important angry.
That's right. It was very strongly suited.
80% in medical. Now, presently we are 80%. In 2014, we were 60%.
Oh, that's
I am talking 24 hours. Forget that 5 days we are not. So
That's good. 60-20% improvement. But right now, we just don't compare with other methods. We just want to say. And then I said, we observed that after 20 days in past, let's improve single and PDF. So looking back actually is important. There is memory there. And in fact, that memory is better extracted from an auto former than from a long shot. Further C ever? Long shot term or time? Term. Okay. What is M stamp? Memory. Yeah, long short term memory. And those were popular earlier to capture long memory and short memory. Transformers, autoformers were better. You see very clearly. Okay, let's carry on. So this is a review quickly. So Rajiv data and long range forecast. This was on a longer time horizon. When we learned that, we saw that yesterday. Taking more from LSTM models were used by Kumar et al. Somebody in the room, let's long list of authors. Reasonably good predictions can only be made up to 2 days in advance, and they were not really comparing with NWP. And again, we've been discussing this more recent architectures, Graph, Climax, I guess there's some other method. The problem with these guys is, well, the difference with these guys is that they're looking at the analysis data and predicting the analysis data. They're saying, okay, we do a very good job of predicting the analysis compared to the numerical weather predictors. Numerical weather predictors look at the analysis data and then they say, okay, 10 days later this. And they train their machine learning model and they say 10 days later that will happen. And then they look at the analysis data 10 days later and that's the ground they compare to. It's not actually what happens on the ground. If you are saying that, okay, IMD data is ground truth and the NWP data does not agree with it, then that comparison is also not entirely valid. They will pay for NWP. But this is in the spirit of what we were discussing last, that maybe we should take those sophisticated models and tune them, fine-tune them to Indian data, more trustworthy ground. Okay, the data sources, IMD daily vivid precipitation data 23. Again, additional variables are taken from CCMWS, daily atmospheric and land data, 1950 onwards, wind temperature, soil moisture, cloud cover, all at this resolution, and existing in the big photograph already mentioned already. Now, focus is on June to September. Now, we probably should ignore, what happens in the very southern tip of India. The monsoon dates are different. Right? I think it's a confusing thing. We didn't do that here. We can be more careful. Okay. IMD data is split into trained data from 1901 to 2011, test data from 2012. We play around with these things. The conclusion is not very sensitive. Have some, For all 6 points, each sample represents 3 contiguous days of rainfall data. I've been saying that. And D varies from 3 to 20. This is the middle, okay? Rainfall is data for T plus 1 day at each point. We use auto forward. Okay, so I'm going to use abbreviation. DLSD means deep learning historical data. So we are using deep learning methods on this point. And we'll extend this to use other covariates, and then we'll say deep learning historical data plus covariates. Yeah. That's right. That's right. So, I mean, if you look at the data of rainfall, you can't really say that it's changed dramatically in the last 10 years. But we also do something else when we train data on last, let's say, so 2010 to 2018, and then we will use it for test the unity base. Nothing changes. Not everything remains the same, so we don't really see that effect. Okay, so covariates, as I mentioned earlier, wind, temperature, soil moisture, cloud cover, humidity, like that. All right, so this is ELSD plus covariance. All right, and these covariance we just use for past 3 days. So apparently, if you go to 4 days, 5 days, it doesn't help at all. You just switch it. All right, experiment HRES NWP plus forecast. So basically, HRES makes a forecast for one grid. Earlier, when we were doing 1 degree by 1 degree, the grids were not exactly matching. Then we said, okay, let's be clever. Let's look at all the neighboring grids and train a network to look at all that information to make a forecast. Let's see how that goes. Now with HRES, the grids were matching, but nonetheless, the idea is what we do is we look at not just one grid, but all the neighboring grids, and train the forecast to these forecasts. In a sense, come up with the right weightage of these forecasts to make the. That's what HRES NWP. It's our way of kind of trying to improve NWP. Okay, NCEP NWP plus is again similarly. NWP plus the data was not available to us. We just came from 2011 to 2020, your point, just from 2021 to 2020. Let's carry on. Ensemble, so we combine everything that we have, DLSD, covariance, forecast, with NWP plus forecast, etc. And then we make a forecast, and that also doesn't. I'll talk about this. I'm just telling you all this notation I'll give you later. Persistent, as I just mentioned to you right now. Whatever happened today will happen tomorrow, or will happen today. So how good is that? All right. So peak bias loss function. So everybody kind of plays on the loss functions. Keep doing that. Okay. Yeah. So we use mean square error. We drew fancy conclusions. We thought they were beginning to make sense, and then things were not beginning to go so well. And a code kind of looked inside the data and showed us that our predictions were just straight lines. Actual performance like this of rainfall, and we are predicting a good straight line which has less error. It's good to look under the hood for these things at city level. And then we kind of said, okay, this is not good at all. So we use this loss function. So whenever the forecast is less than the actual reading, so RT is the reading at time t, R hat t is the forecast at time t. Whenever we are underestimating, we don't like that. We want to penalize that. We don't want to underestimate anybody. That's not about that. So we penalize that error by raising to the power 1.5. Whenever we are overestimating, we just take the absolute value. And this is again with experimentation. 1.5 we played around, okay, 1.6, 1.4, 1.3. This works quite well. So this is our loss basically. This is the loss function we are calling it, and we're calling it peak bias loss. I think we just ran out of ideas of what I need. In all our experiments, this was a pretty good. So that's what we did. And we use it everywhere. But we'll also, once we train it to this, we seem to be chasing the trend much better. So then we'll report that mean square error also of the best answer that we get. And they follow the similar trend. That's interesting. I don't know what to make of that. All right, so these are our results. So comparison for 1 day forecast. So DLSD covariance gives you a peak loss of 18.24, which is while DLSD just looking at past data gives you 20.90, so about 14.5% versus this guy. Just HRES NWP, which is a pretty good NWP, so it's about 22% worse off. And then all these other numbers. Ensemble is again not doing as well as the DLHP covariance. You think by keeping more covariance, you increase the options, but you've not taken away the option that was already there. But just with training and test data, that's not how things work. Yeah. Yeah, you're saying something else, but at the end, in some sense, proof of the pudding was looking at the picture. So I'll talk about that. You'll see what there's a big difference in what you see forecast by this method vis-a-vis forecast by this method. It's clear that you're capturing something more fundamental. But yeah, we tried variety of loss functions. It's not like something surprising. Orders. This you can see the mean square error also follows the same pattern. All right. This is just as I guess Sanjeev was saying, this randomly chosen day, July 15, 2022. This is the ground truth the next day. This is how India looks like. This is DLST plus covariance. So reasonable job, not that great, but reasonable job, and there are actually error numbers are here. This is just DLST, slightly worse off. This is if you see HRES. Generally, these numerical weather predictors overestimate always. They make errors on the higher. And sample is yeah, that's higher error only. These things depend day by day, but in the average numbers. Okay, for 3-day forecast, so again, our error is 67.2. What is again this peak bias now? Average over the day. 4,500. July 15th, we have 4,000 grid per variant we make. Main numbers there. Okay, so you can see here that the numbers overall are of course higher, and but we are doing better than other methods compared to NWP 27%, compared to persistence 70%. Okay, so there's value to looking at just actual rainfall data. I guess that's kind of the. Particularly if you're going to test yourself, evaluate yourself against the real actual rainfall data. But that's what we want to evaluate ourselves. Okay, so this is comparison 3 days ahead. Again, this is the true ground truth. This is the covariance, slightly worse off and these are. Okay, now these pictures are somewhat interesting. So this is Mumbai now. So this is blue is actual rainfall. This is July to August again 2022. So blue is actually how the rainfall happened in Mumbai, and red is the forecast that we made. So it's not terrible, right? I mean, these are again, I don't know, can you use them as the operational thing? Yeah. Sounds odd because Mumbai, we're not even looking at Arabian Sea. Maybe rainfall in the Arabian Sea will have some information which is useful to Mumbai. So we're not even looking at that. It's probably just but still, I mean, persistence error gives quite high. Persistence error is 1, and this is 50. So we are much better than just saying what happened yesterday. All right. This is what the numerical weather predictor does. So you can see a lot of overestimation, but quite missing the point. This you can't improve by changing loss function. Again, we can again, these are the numerical weather predictors adjusted. Again, they're missing. Example does well, not as well as we do, but that's because this is one of the covariates in that sum. But I'm showing you Mumbai because probably I think in Mumbai we got the best match. 3-day forecast. Not too bad for 3-day also for Mumbai. But other methods are before. Example is almost it. Although the error is quite high. Okay, now this is for Chennai. So now I'm thinking that maybe we should not have done Chennai. Chennai is being governed by different monsoons, October to December. Why look at data from June to September for Chennai? But in any case, see, so here also we are doing a better way. And this is Chennai for 3 days. Basically, everybody is not going to Chennai. This is for Ahmedabad. So, I mean, yeah, you can't go live with these things. You can't use these to make forecasts. You can't make this to make predictions. But that's why I feel that actual rainfall is important. But certainly the bigger point is that one cannot rely on numerical weather predictors, and they need to get more data. So satellite information, data information, and then we can compare to all this and see where we are. Okay, so predicting heavy rainfall and for the rate. So again, given that actual rainfall next day is more than 30 mm, the model predicts that it's more than 10 years. It's going in the right direction. Given that the actual rainfall in the next 3 days is more than 30 mm, the model predicts that it's less than 30. This should be less. No, this is for 3 days. The next 3 days, this should be 60 and this should be 20. It's actually more than 60 and the model has more than. Yeah. All the lab ranges are just one. Okay, so while NCP does do a good job of heavy rain prediction, but they're always over predicting. So whenever the actual rainfall is more, they're also going to say it's going quite high. So you won't make a mistake. But then they have a very high false alarm rate. They say it's high, but actually it's quite low. So that's going to be very high there. We do a good job on both the measures. And we have a much better correlation with the down to compared to other. So let me just show the number here. So our false alarm rate is 27%, while the NWP's false alarm rate was 21.2. It's quite high. So we're better than our high rainfall prediction rate is 82.24%. So 82. So even this warning, if you want to give, it's actually more than 30% and 30 millimeter, and you say more than 10 millimeter. You're only right 80% of the time. Even there, you're making substantial mistakes. This is not the way to go. But nonetheless, 82% for us, and then the carriers in the WP is. It's just all these 3-4 indexes you put together. They all make a forecast. We look at the linear combination of them, which does but some neural network combination of them, which makes it better. So all of these are in the 80s, so they're equally good now. All very same. And persistence, of course, is way off in both of them. And the correlation coefficient, we get 82%, while NWPs, for example, have 69. And this is the best NWP of the study. And same things hold for 3 day things. So our false alarm rate is 37%, which is not terrible for 3 days. There are high rainfall ratios 74.8%. This for NWP here, 41.39%. Our correlation coefficient is 64% and all right. So then the other question is there memory in the data? So this is if you use LSTM. Now we're looking at peak bias loss as a function of how many days we use in our data to make train the network. If we had used LSTM, our error would have been high and it would have come down only slightly as we use more data. So with transformer, it comes down substantially. This should be significant in every sense. The transformers are better at capturing patterns, hidden patterns. That's interesting. And also you can see that if you had just stopped at 8 days, you would have been at much higher loss of income. It's substantial decrease. This is useful that it does make us to go back at least to, let's say, 15 days. All right, and this is now looking at this thing for landlocked cities and for coastal cities. Same thing. This is for the coastal city of Mumbai. So 1 day would have been enough. 1 or 2 days would have been enough. It didn't make any sense to go back 20 days. Which makes sense. It's a coastal city. Most information you need is not available to you. It's out in the coast. So this could be a good project that now you look at reanalysis data out in an Arabian Sea. See if that's useful to the Mumbai one. That they did not do. And the same thing with this, I guess, is Kolkata. Same problem there. And for other cities, for example, this city is Bangalore, you begin to see some. They are too small to really make a big deal of. Then also you see some improvement in the landlocked cities, you see some improvement by having more. So we did this for coastal India. So this is just 60 kilometers from the boundary. See, we looked at the grids here, and then we trained them using historical data, number of days, and you see, okay, you get only a minor benefit using lots of past data. But if you look at the landlocked region inside it, there you do see that, okay, you get substantial. So that is making the case that there is information inside within the neighborhood basically. Here we have the neighborhoods available. Out here it's not available out here because you don't get data from neighbors. I don't know. Okay, so other thing was how do we select covariates? We did a greedy algorithm, no point doing all a combinatorial search of all covariates to find the best subset. We just found that okay, precipitation is obviously important, so we take that. So now if we take precipitation tau cover, what's that error going to be? We take tau cover, precipitation plus horizontal winds, what will that error be? Vertical winds, temperature, humidity, soil moisture, so on. So we look like this and we take the best one. Then we fix these two, precipitation and tau cover. Then we do that with the remaining variables and we find the soil moisture. That's something here. That's how we decide. I mean, one can do this nitpicking. There's not much. Okay, so that's all I really have to say. So advantage of ML techniques. So it improves upon numerical weather predictors. This is kind of known, but it's good to say how much and where. I think there what we're saying is kind of across the board the improvement is. That's what we see. And about 20% is as well. R error measure as well as well. Better integration by cost varying variables enhance predictions. So just rainfall data is not enough. Covariates do help. Potential for operational use in better program. We should aim, and this could be the part of our next section. How do we bring these things to be much better than they are? What extra information do we need to make it much better? I think we should have a clear benchmark. So that's all we have to say right now. I think what I can add is that some students' village is doing similar analysis with temperature, but I guess I'll hold on and not say. Thank you. Of course. Sounds good. You saw substantial improvement?
But not on weather. We looked at electricity consumption data. We looked at it from other kinds of. So,
do you have enough training data? I mean, probably this point in some sense it's very sparse data, but there is so much to extract from it. Great, yeah.
very good.
No, but that's better.
Special. It was not. But we also found very interesting thing. While you saw in many cases that it is dipping like this one, yeah. We saw curves like U curve, saying that if you go beyond a certain point in time, then that spoiling the prediction.
This is on the test data.
No,
No, it's, but on the test data you see this. So we didn't see that. I mean, that's what it'd be interesting to see if there's still more information. We can bring this down further.
that you convert this data to image. No, just artificially. Create some feature. From the features, create a feature.
So each day we have one feature.
Each point which has got several features on it, that will have feature.
I mean, there is a picture of rainfall that happened in our million. You just take that picture. Well, yeah, one can kind of spread these numbers. And there's continuity also there. They actually do maybe use. So what we've done from this, images have you got a massive storage, right? And there's a massive amount of input that you're feeding. Here, just using 4,500 per day, maybe 45,000 data volume. That's a year. No, 0.251. So I'm using very sparse data if I'm sharing. That's right. So my question is, so that's where we want to go. Now we want to gather all those images, store them here. Do we just throw the complete image into a neural network, or do we extract some features and throw the small pieces into it? So the whole thing.
Yes, I told you, first we extract from the image.
That's right.
Using just available software. And we ran it first. Then we did pure image. We ran it. And then we took the features of the image, took the features, extracted separately, concatenated them, and
But the timing would be very different, right? And training time, when you just take features, it will be much faster.
yeah, but
But you get better. Yeah. Just take the image itself. It's not already there. It's very good information in the whole thing. So I think the whole, what's interesting what you're saying is right now we're just taking this matrix, this because matrix of university again, you're not even giving it geographical information. You're not telling it this guy here, this guy here. But the image, I guess you are in some sense. Probably there's some geography going in.
lot of smoothing can be done. That's exactly what it is. Lot of good smoothing techniques applied, and then you take the image and put it there. How to get some interesting.
Where is towards the end, talk about how you divide it up and box and see. I think because you have quite a lot of data, you probably introduce a little more realistic division. For example, Deccan Plateau is very different from the Northern Indian plains. You have the Western Ghats and the Western Ghats are different from each other. Stuff like that. So maybe divide up into, rather than lump the Deccan Plateau together with the plains, like Kannur and Pune together. I mean, we don't really understand now how to do that division. That would be a qualified division. Knowledge comes. That's it. That's it. That would be a qualified division.
I
Two things like that.
elevation, distance from the sea. You just add these features, you don't even have to write out a here. And he's asking now, what are the covariates? Yeah, distance from the sea. Actually,
Yeah, when you kind of ask yourself, okay, why is something influencing rainfall 10 days later? So it should be in the right direction that much stay away. Maybe those things should get higher rate. Then right now we're moving the network is figuring it out.
it's figuring it out. But I think the more complex you add, like Mumbai and others, you will see how much is this one and the geographical correlation. And then comes the neuro GCM model. You can apply that the neuro GCM model does the graph convolution network which you were talking about on this problem that is suggested. Once we have the neuro GCM model, then we solve this one.
It's also exploiting the geometry, right? Yeah.
Neighbors.
That's right.
All the neighboring cells, it goes on learning and creates its own network based on the neighboring.
Neighbor also temporal, not just spatial.
Spatial temporal learning will happen in that, I think you will get significantly improved.
That's all. That's all. And thank you so much. Yeah. Any other comments? Okay, so I'm going to request PPC to take over. Yeah, but I just want to take this time also to thank particularly Sneh for all the hard work. Also Shivani and the make this hard work. So thank you. Today is the new Shivani for the
Okay, so I am PPC, Dr. Chakravarti from IT Kharagpur. I'm an advisor to computer science at Ashoka, also part of the advisory board of this. So the objective of this last few minutes is to figure out the way forward. And we've been discussing it throughout this. The first thing we in that the Ministry of Science and the other institutes, they have some very interesting problems to solve. She talked about problems. Ceremony, we talked about structural moving. So I think the first thing we should do is discover the problems. And the second thing is that they have this storehouse of data. So we have already discussed that if we are able to have a detailed discussion about what we want to do, MOU, in the signing such MOU, we will get access to data for use of our. Thirdly, we've had some very interesting partnership thoughts, both from Sukumar and Jayan. Narup Ganguly, who spoke yesterday, he's a master of all. So in terms of taking all this, I didn't hear the other one, but he's occupied. And he's fairly willing because he's working with the MOES, he's integrating all the machine learning algorithms into the MOES algorithm. He works with and he has a very good team, and his students are now faculty of IITs and therefore I think that we should set up a collaboration. And we should identify some of the most important problems that we want to address, where we can improve the speed, improve the accuracy, improve the explanation, because bringing in the physics into the explanations are very important. So I would request that the experts who have come, at least we should have a follow-up meeting. My first request is that if each of you can write up a small, and we'll ask the others also about what they think we can do, what they think that this center can do. Parallelly, we should have an immediate meeting with the IMD and DGMI. Huh? DGMI. Right. So he said, contact
and we have a format for MOU.
They have a format for MOU. Once we get the MOU, we have the data. Once we have the data and everything else, then we should do 2, 3 things. This is my thought process. One is I've been working with the AI students of Ashoka and faculty. And I think if we give these students projects, small projects to do, and link them up with our students in Adirani or Kharagpur, I think it's such a low cost investment by which publications can come out on the data. And then that is the first thing we should start publishing on some joint publication coming out on the use of this and on various. And the next thing is that maybe within 6 months down the line, we will have an idea of at least a moderate and gives to some funding agency, whether IMD and get that proposal up for a good research program which integrates in science, the AI tool into the. Finally, I think we should have a course on rather than by course. Data science which would be a course which would be good thing from the center and by creating a little we are trying to come up and major in data science of the program. So that will also be a very yeah. No, we can see that.